Hello, sir.
Yeah, I'm not able to. Oh, okay, great. Yeah.
Hello, sir. Good morning. My name is Harita, and I'll be moderating your session today.
Thank you, Harita. So you are in IISER Bhopal?
Yes, yes. So we'll start at 10 o'clock.
Yeah, sure.
Yeah. Did you have anything?
Oh, no, I did not have anything at all. So you are a research scholar there or faculty or?
Sorry, I'm a student, sir.
You are a student. What are you
Yeah.
studying?
I'm doing my PhD now.
Great. Okay,
Yeah.
what's the topic?
I'm working on dynamical systems and ergodic theory.
Oh, wow. Very
Yeah.
good. I see. Very good.
Thank you, sir. So we'll start at 10 o'clock.
Yes.
So I think everything is all right.
Okay.
Yeah.
Yeah. Right. So is it a topological dynamical system or measure theoretic or?
A measure theoretic.
I see.
Yeah.
I see. And does it have anything to do with mixing, transformations, and so on? Or
So I'm basically working on symbolic dynamics. So on symbol spaces, and it includes combinatorics as well.
right. I see. Okay. Uh-huh. So you will get some Markov chains and such things.
Yes. Yeah, precisely that.
Right. Exactly.
Yes. So I'm a student of Dr. Nikita Agarwal.
Oh, I see. Oh, very nice. Very nice. I see. Mhm. Yeah.
So there is a comment in the chat box
Correct.
from Ramakrishnan saying he has a doubt in yes.
Correct. Why not ask? Yeah, sure, ask.
So probably you can discuss with him now. So I'll unmute him.
Okay, fine.
Yeah.
Hi, I've unmuted myself.
Yeah,
Good morning,
sure.
sir.
Morning, ask me.
So this is with regard to the definition of a poset which you had given.
Yeah.
So suppose you consider the subset, all the subsets of real numbers, and you consider strict inclusion.
Yes.
So according to the first definition which we started, it would be a poset with this relation.
Correct.
But then we proved another three set of axioms saying that many a place those three are taken as the definition of poset.
But wait a minute. The other thing is denoted by less than or equal to.
Exactly. So we said there is so one induces the other. So if we start from the strict inequality, it induces this less than or equal to, and the vice versa. But this object, the set of all the subsets of real numbers, along with strict inclusion, according to one definition, it will be a poset, whereas with respect to the other, it won't be.
What other? What is the other?
So this, no. So if suppose I just have all the subsets of real numbers with this strict inclusion.
Yes.
And if we have to verify if this is a poset or not,
correct.
Which of these two definitions would we go by?
Wait a minute. You see, okay, it is just like thing. Somebody is speaking in English and somebody is speaking in Hindi. Okay? You don't compare them, you will convert, right? One is the other. Exactly. Okay? In the same way, if you started with less than definition, okay?
Yes.
You see, that think of it like English. And less than or equal to is like Hindi. Okay? Suppose somebody is talking in English, then how do you convert it to Hindi? You see? So if somebody defines x less than y on a set, okay, then you say, okay, all right. I say x less than or equal to y if x is less than y or x is equal to y. That is my new English thing. So it satisfies those three conditions, right?
Yes.
So it all depends on, okay, the reason I mentioned that is because in some books you see less than, in some other books you see less than or equal to. Okay, and you should never get confused. It is just like speaking in English or Hindi. Okay?
Yes. Okay.
So you have to convert.
Okay.
So if you take all subsets of the real line, A is strictly included in B. That is a partial order according to definition 1. Okay. But
Yes.
if you want to use definition 2, then you have to define A less than or equal to B if A is contained in B or A is equal to B. Then it
Yes.
satisfies the other. Yeah, that's it. It is a language. That's all.
Okay.
Yeah, very
Okay.
good.
Thank you.
Yeah.
So, okay, we'll wait for 3 more minutes and then start.
Oh, yeah, sure, we'll wait. Definitely. Yeah.
Good morning, Bibi.
Morning, Shashi. How are you?
I'm fine.
Good.
I have a question too.
Yeah.
If one learns complex analysis, is it prevented from learning algebraic topology?
No, I don't think so.
Then why for set theory?
What? But
if one learns set theory.
No, axiomatic set theory. Wait. I never said set theory. Axiomatic set theory. You see, if you start stating the axioms, okay?
No. I understand. Logic comes little later because logic is requires more maturity and patience. It should be at the master's level. But I think some amount of set theory, naive set theory, cardinal arithmetic, axiom of choice, John's lemma, there should be a small course in set theory in the beginning.
Of course. Yeah.
What is naive set theory or what Cantor discovered?
Right. Sure.
And I think not knowing transfinite induction, that was the main discovery of Cantor.
Right.
And that I consider very fundamental for mathematics.
Oh yeah, sure, it is.
Okay. So I misunderstood you. I thought that if you learn set theory, if we start taking set theory, then you will not learn other mathematics.
No.
Learning one thing prevents. How did I learn so much of other mathematics? Did you only teach me set theory?
No. You see, the point is
you taught me so many things other than set theory.
Yeah. So axiomatic set theory is what
you see my mobile for you.
So and you see, as I said, the analogy is the following. You can learn a little bit of set theory. Okay? It is just like you learn a little bit about colors. But if you want somebody to define what exactly is color, it is a disaster.
Yes.
That's all. That's what I said.
Yeah, so it should everything comes in stages, you know. You don't start functional analysis right in the first course at BSc first year.
Sure.
So slowly at each level, things have to be taught. And I think this is a big mix. Now logic is playing a very, very useful role in solving outstanding problems in mathematics. There are a lot of model theorists who are making a big
Sure.
Number theory and algebraic geometry.
Sure. Definitely.
Okay, so now I leave you. It is your time.
Okay.
I am muting myself.
That's okay. You don't have to mute. And
okay. So I think it's time, sir.
Okay.
So good morning, everyone. Welcome to the second day of ISLA 2020. So we have, my name is Harita and I'll be moderating the morning session for today. So the first talk is by Professor B.V. Rao and he'll be continuing his lecture on set theory. So handing over to you, sir.
Thank you. Okay, so first I will recall what we have done yesterday, and what I am showing here is different from what I am saying. So let me read what I am showing here. Shortly before the end of his life, Swami Vivekananda fell ill. During his convalescence, he had begun reading the newly published edition of the Encyclopedia Britannica. His disciple, Sarat Chandra Chakravarti, seeing one day these 25 large volumes, remarked, "It is difficult to master the contents of so many volumes in one life." He did not know at that time that Swami had already finished 10 volumes and was reading the 11th. Okay. So you see. Okay. So yesterday, I started with axiom of choice. Then I first explained why. We separate out the axiom of choice and discuss about it. Okay. Not the others. Then I gave some equivalent definitions of the axiom of choice. Okay. And one of them is John's lemma, and one of them is Velapidan principle. I showed you one direction in their equivalence. We will go to the other direction later. But yesterday, there was a question. Oh, by the way, so yesterday, I stopped my lecture at 3:45, but today I will stop 5 minutes before and then we shall go through questions. Okay? All right. Yesterday I said two sets XY not empty. Okay? Then you can pick points from each of them. You do not need axiom of choice. In applying John's lemma, we needed this. I said add constant symbols A and B to your language. Add axioms A belongs to X, B belongs to Y, and work. Whatever you conclude in this theory can be done without these symbols and axioms, but just using X not empty, Y not empty in the original theory. That is what I said. Okay? And I said the reasons lie in logic briefly, but since I did not explain what exactly is the logic, Dhruv Bhashin from, I think, IISER Pune asked, why can you not do the same for a family of sets? For example, I have a sequence x1, x2, etc. not empty. Why don't you add constants a1, a2, etc. and axioms? A1 belongs to x1, a2 belongs to x2, a3 belongs to x3, and so on. Okay? Very legitimate question. And of course, because I did not explain the reasons are involved in our logic, okay, he correctly asked this question. So I can't get over that. So let me explain. So when you do this one, axioms, you are adding infinitely many axioms. Okay? But anything you prove has a proof of finite length. You would be using only finitely many of these axioms. No problem. You can do that. But remember, you can never prove anything that uses all these infinitely many sentences. Therefore, all this A1, A2, A3, etc., which you have supposedly got, okay, by choice function are not at your disposal. Thus, just by imitating, you will not have at your disposal all these AI. Then what is the alternative? You want to add axiom of infinite length. A1 belongs to x1 and A2 belongs to x2 and A3 belongs to x3 and A4 belongs to x4, etc. At one stroke? No, our formulae are of finite length. Or you want to add one sentence for all I, AI belongs to xi. No, the quantifier for all I is not at your disposal. Okay? So you cannot do anything, and that is precisely what the thing, because of our logic, that phrase explains. Okay? Therefore, you cannot do with infinitely many sets. Okay? But if you still have questions, you do not have to accept anything. If you still have questions, you can please raise and we shall discuss. Okay?
Divi, can I intervene a bit?
Yeah.
how about using induction and so that for all n, if we have a family of n many non-empty sets, then there is a choice function.
Yes,
this only requires ZF axioms.
And this only needs
ZF axioms. Germelo-Frankel.
No.
Induction is true in ZF.
Yeah, right.
And so for n equal to 1, the set X is non-empty. So it means that it automatically shows there exists a point.
Yes.
And then if you take n plus 1 many sets, non-empty sets,
yes,
then by your induction hypothesis, for the first n you have already got. And the last one, an plus 1 is non-empty.
Right.
So by definition, there is a point.
Yeah.
So extend the function.
Wait. So, but you are adding all these infinitely many sentences, and in your proof, you are using infinitely many sentences. That is not allowed, right?
No, I am not adding any sentences.
Then
I am saying that induction is a theorem of Germelo-Frankel axiom, Germelo-Frankel set theory.
Right. Yeah.
And then I have for each n I have a statement.
Yeah.
And then whatever n you fix by induction, you show that all those statements are true. It is not saying that the infinite thing has a choice function.
No. So for every, you see, there is no problem. For every n, you will get for exponent to xn. That's all. But you don't get for all of them.
No, I didn't say for all of them. I only said that finite axiom of choice can be proved by
sorry. Sure. Finite axiom of choice can be proved. Yeah, sure.
By induction.
Absolutely.
And induction is a theorem of the Germelo-Frankel set theory. It does not use axiom.
Okay, sure. You can do that too.
So that is a better way than going into logic, I thought.
Oh, yes. You can do by induction too. Okay? Yeah.
So,
yeah.
So why don't we have the for all quantifier?
Pardon me? Oh, because your logic does not allow for all I. You see?
For this year.
Yeah.
Okay. So okay.
So can you explain it again? How logic is related?
Pardon me?
So can you explain it again? So how you relate it with logics or axioms, all these things?
Yes. That is because
The upper portion which you explain it.
Yeah, sure. So you see, if you want to select for an infinite sequence, okay, number one, you have to extend. And you have to say A1 belongs to X1, A2 belongs to X2, etc. so on. Okay? And that is why the problem. Okay? Anyway, you think about it, but you don't have to accept. Okay? We will still discuss about it.
I think it will become clear in logic lectures once they learn some logic, what you are saying.
You see, basically, our formulae are of finite length.
Right.
And our proofs are of finite length. We don't allow any proof of infinite length. Okay? And in fact, this is one of the things usually we don't stress when we explain method of mathematical induction. So you prove for 1, you prove for 2, you prove for 3, and common sense says so on. Okay? So on is right. So what do you mean by so on? Are you going to write infinitely many proofs for every n? Then you have not proved for all n it is true. You see? So that is the beauty of mathematical induction. Okay? Yeah.
Yes.
Sir, sorry to interrupt you. It would be good for all of us if you could turn on your video.
Oh, wait a minute. Did you not turn? Oh,
no, it's off. Yeah.
I'm sorry. Wait a minute. I don't know where I should do that. Let me see. Okay.
So you have to.
How do I go back?
So it's full screen now, I think.
Oh, great. Okay, now I see that. Okay, fine.
Thank you, sir.
Oh, I didn't realize that. Oh, wow.
That's fine.
Okay, fine. Thank you.
Sir, can you explain once again why can't we use the for all quantifier?
Okay, you find out what is the definition of formula. Definition of formula is, okay. Oh, wait a minute. Yeah, okay. Definition of formula is there exists x, phi x, for all x, phi x. Okay? You never have there exists I, phi I, or for all I, phi I, right? So that's the problem. You see? So you have to understand the logic, how we have built up our methods of arguments. Is it okay? Or is there any problem? You see, you go to the definition of formula, definition of proof. Okay? Definition of language, formula, proof. In set theory, the language is just variables, x1, x2, or you can call xy, and epsilon is the symbol. And then you can only use there exists x, phi x and such things. Or there exists x belonging to y, phi x. That is same as there exists x, x in y, and phi x. Is it okay?
Yes, sir.
Yeah, but think about
Hello, sir.
Think about it. Yeah.
Sir, are you saying you can't use there exists xi for all I in some index set?
What?
Are you saying you can't use there exists xi for all I?
No. You see, the point is the following. There exists I belonging to delta. This kind of thing you can use. Okay? But there, remember, you are using a formula in your theory. Okay? So, this there exists I belonging to delta. Okay?
Yes, sir.
You can definitely use it. Okay?
No, you said something about for all quantifier. Right? Like, can you please repeat that?
When you are discussing, you see, when you make a statement, you have to first make a statement and then you prove the statement, right?
Yes, sir.
Now, when you make the axiom of choice, okay, you are saying for every family of sets, there is a choice function, right?
Yes, sir.
You see? So that is the problem. For all x, there is no for all I. Okay?
Okay, sir.
Anyway, think about it. Okay, all the questions are very valid questions. Absolutely. There is tremendous confusion about axiom of choice, and that is something at least we should clear by the time the lectures end. Okay, and we should not be in the same state at the end of the lectures. Okay, yeah. Okay, so think about it. We'll discuss again. Okay. So now, to continue with what I was doing last time, okay, now what happened? Wait a minute. My screen has gone, disappeared. I don't know what happened. Okay, fine. Yeah, okay, fine. Okay. So are you able to see now my screen?
Yes, sir.
Yes, sir.
We can.
Okay, fine. Got it. Now, yesterday I stopped at this point. If f is a filter on a set x, we can extend it to an ultra filter. And that has an interesting property. If you take the set of integers, for example, then the cofinite filter can be extended to an ultra filter that will give you a measure which takes two values 0, 1, but it is finitely additive. And okay, then I said about sigma filters. A filter is closed under finite intersections. You can talk about sigma filter. Filters closed under countable intersections. Are there such things at all? Yes. Here is an example. Take any point x, look at all subsets of your capital X which include this point little x. Then this is a filter. It is closed under arbitrary intersections. Okay. Therefore, there are sigma filters.
Hello, sir.
Yeah.
Hello, sir.
Yeah.
I'm very sorry to interrupt, but yesterday I couldn't follow what you said. I mean, what is the definition of filter and ultra filter? I'm sorry I interrupted.
Yeah. No, definitely. You see, a filter is a collection of, suppose you have a non-empty set X, okay? And take a collection of subsets of X which satisfies three conditions. Empty set should not be there. If two sets are there, their intersection is there. If a set is there, any superset is there. Okay? Forget about the symbols A, B nonsense. So, it is closed under intersections and supersets. It should not be all subsets. That's all. Is it okay?
Yes, sir. Yeah.
Yeah, it should not be all subsets, but it should be closed under intersections and supersets. So, for example, if you take all subsets containing this point little x, then this collection is closed under intersections and supersets, obviously. It is not all subsets. Empty set is not here anyway. Therefore, this is a filter which is closed under countable intersections. Okay. Now, you can ask whether there are other sigma ultra filters. Okay. Is there a sigma ultra filter which is not like this? That means if you take any point x, singleton x complement is your ultra filter. And I said, so this is what I said yesterday. This question already leads to deep set theoretical problems. You cannot prove their existence. You cannot even prove consistency of their existence. Okay. This is a higher level. You see, already at the beginning, there are deep problems. When you look at axiom of choice, that is a problem. You cannot prove it, but you can prove that it is consistent. Okay. Of course, all the results are assuming that ZF itself is consistent. To start with, if ZF is inconsistent, then everything is a consequence. Okay. So that is basic assumption. So you cannot prove AC, but you can prove the axiom of choice is consistent with other axioms. It does not lead to any contradiction. But this statement, namely, there is a sigma ultra filter which is not of the type I mentioned. You cannot prove its existence, and you cannot prove that the statement is consistent either. Okay? All right. But these are deep logical problems. We shall not enter, but I just wanted to show that even at the elementary level, there are complicated things. Okay. And let me tell you, the standard terminology for sigma ultra filter is countably complete ultra filter. Okay. Nobody calls it sigma ultra filter. And this is notation is used, especially when you want to generalize to higher cardinalities. But we shall not enter into that discussion. Our objective, we are heading to showing that the other properties I said equivalent to axiom of choice are actually equivalent. And for that, I said we need vocabulary, ordinal numbers. Okay. So I shall follow that. It is hard to say uncountable well-ordered sets, though there are plenty and unending. Okay. It is easy to see countable well-ordered sets. For example, this usual order is a well-ordered set. You can see other thing also, 0, 1, 2, up to n. You see, include infinity, infinity plus 1, infinity plus 2. Stop there. That is a well-ordered set. You might ask me, what are you saying? What is the order? Of course, I leave it for your imagination. 0 is less than 1, 1 is less than 2. These are all less than infinity. It is less than infinity plus 1, it is less than infinity plus 2. That's it. You can show, okay, very simple exercise, every non-empty subset here as a first element. Now, you will ask, what the hell is infinity? What the hell is infinity plus 1? I know what is 4 plus 5. Now here, as I said, the plus symbol is at this stage only an illusion. Okay. There is no meaning for the plus symbol. If you wanted, you could have written 0, 1, 2, all integers, and then BB Rao here, and then Shashimohan here, and then Amit Kuber here, and so on. That's it. These are the things. Or here is another example: 0, 1, 2, infinity, infinity plus 1, infinity plus 2, infinity plus 4, 5, 6, right? And finally, you put infinity plus infinity also. This is also a well-ordered set. You can easily show that. I leave it as a simple exercise. You do not have to take any pen and paper. You keep on staring at your set and imagine non-empty subset of this, okay? If it has any point here, you can always find out. If it has a point here, you can find out, and so on, okay? All right. But this infinity here, unfortunately, we are familiar in real life as n tends to infinity, as x tends to infinity. Therefore, I don't want you to confuse that I am using this symbol infinity. I will change it to omega. So these sets, I will write 0, 1, 2, omega, omega plus 1, omega plus 2. Okay. Omega, omega plus 1, omega plus 2, and so on.
Hello, sir.
Yeah.
Sir, do you progress in the sequence by taking unions or something?
What do I?
Like progress in the sequence by taking.
Very good. Exactly. But I will describe to you. Right now, our main objective is to make this thought process very precise. Okay, very good. I will make this thought process precise. Okay. I started with integers. Then I said you can add at the end. Then you can add, continue adding. Okay. I will make it precise in a minute. Very good. At this moment, it is not at all clear what the hell I have in mind. But at least intuitively, it is clear for you that the well-ordered sets are unending. You can continue adding. Okay?
Hello, sir. I had like one more doubt.
Yeah.
Suppose you take the union of all 1, 2 up to n.
Yeah.
Okay, then you'll get the next level. But then how do you go from that level to the next level? Because if you add like whatever finite union you take, it's still going to be the same level itself.
No, you keep on continuing. You will get all integers. Then you will get the set of all integers you will put. I am going to explain right now. Okay? This is only an intuitive idea. Whenever you think of a well-ordered set, please think of people standing in a line. Okay? One, next one, and so on. Okay? I will make it precise. I will define all these things. This is not at all rigorous. Okay? I said so on, so on. This so on is a very dangerous word. Okay? And there used to be an exhibit in the IBM Museum in Chicago. And the statement, every odd number is a prime. A chemist says, okay, 1, 3, okay, every odd number is a 5. A physicist comes, okay, 1, 3, 5, 7, all odd numbers are prime. So on. And a statistician comes, 1, 3, 5, 7, 9, experimental error, 11, 13, prime. Okay, experimental error, otherwise all odd numbers are prime. So you see, if you say so on, you can be misled. I have used the word so on, you can add, okay? That is not at all correct. I will make everything precise right now, okay? And mathematics, you should keep in mind, is only making precise what you have felt, okay? We will make this precise now. Let W be a well-ordered subset. A subset of W of the form x less than A for some A in W is called an initial segment. For example, if you have the integers 0, 1, 2, 3, 4, 5, etc., 0, 1, 2, 3 is an initial segment determined by 4. But 1, 2, 3 is not an initial segment. It is missing 0. Okay? So, W is not an initial segment of W. It is a whole of W. Okay? So, initial segment means you take a point in your set, look at all things strictly below that. That is called an initial segment. Okay. Here is a subtle point. Okay. We are going to talk about order preserving maps between well-ordered sets, and after defining order preserving maps and certain relations, okay, what I am going to do is the following. I will make precise what is this, so on and so on, number one. I will show you that every well-ordered set is isomorphic to one of the things I am going to show you right now. Okay? These are the two things I will achieve. Okay. So let us first of all discuss some properties of well-ordered sets. Then we shall discuss special well-ordered sets, which will be these things. Okay? Very precisely. Okay. Suppose you have two well-ordered sets. An order-preserving map between them, okay, is a function from here to here, which preserves the order. Okay, which preserves the order. Whenever x less than y here, then fx is less than fy here. Okay, and an isomorphism is a bijection which preserves the order. And if you have that of this set to itself, it is called automorphism. So, order-preserving map, isomorphism, automorphism. Okay. Now, yesterday I said some people define partial order using less than or equal to. Okay. Now, please remember, I am starting with less than, not less than or equal to. Okay. If you have order-preserving map between these two things, it means whenever x is less than or equal to y here, fx is less than or equal to fy. Therefore, the constant map will be order preserving easily. But please, that is not order preserving for us, because I said order preserving between these things. If x is less than y, fx is less than fy. Therefore, it should 1 to 1. Okay? All right. So now let us we'll observe a few properties of these maps. Then I will show you lots of well-ordered sets, don't worry. Suppose, so at this moment, because you have not seen too many well-ordered sets, you think of a well-ordered set as people standing in a line, the first fellow 0, next fellow 1, and so on. Okay. So f from w to w is an increasing function. Okay. That is x less than y implies fx is less than fy. Then fx is always greater than or equal to x. Okay. That means x is less than or equal to fx. How do you remember that? Any order preserving map, okay, pushes a point up. It will not push a point down. Okay. X is the point, fx is always up. Okay. Now, please notice, if you take unit interval, look at the function fx equal to x square. It is order preserving, but it pushes points down. Okay. 1/4 goes to 1 by 16. Okay. So that happens. But in a well-ordered set, any order preserving map can only take you up, not down. Okay. Proof is very simple. Look at the set of all points where fx is less than x. Okay. Now, if it is not empty, I want to show it is empty. Okay. If it is not empty, let us take the first point. Now you see how the definition of well-order comes into effect. Take the first point u here. Okay. Then, I called it z. Okay. Take the first point z here. Then fz is less than z, right? Suppose I denote this fz by u. Then u is less than z. F of u is less than f of z. That means f of u is less than u. Okay. Just look at this equation, inequality. Denote fz by u. U is less than z, and fu is less than f of z, which is u. Therefore, u is a candidate in this set. How come? You said z is the smallest element. So that is the contradiction. Now, you see, this is a beautiful series. A movie develops out of it. If f is an automorphism of w, then it must be identity map. Wow. If you take the unit interval, fx equal to x square, x cube, they are all automorphisms. They are all 1 to 1 order preserving maps. But if you take a well-ordered set, if you have an automorphism, it must be identity map. There is nothing else. Proof is obvious. You don't have to read here. Because F pushes a point up. Okay. And F inverse is also automorphism. You see, if you have automorphism F, then F inverse is also automorphism. Okay. Obvious. Therefore, F inverse also pushes it up. That completes the proof. Okay. So let me quickly read out. We said X is less than or equal to Fx. Y is also less than or equal to F inverse Y. If I take Y to be Fx here, this will say Fx is less than or equal to F inverse of Fx, that is X. Therefore, Fx is X. Okay. If two well-ordered sets are isomorphic, then the isomorphism is unique. Now, do you see the beauty? There is no choice anywhere. Okay. Sorry. So, if you have two well-ordered sets, if they are isomorphic, ordered isomorphic, then the isomorphism is just unique. There is no choice for you. Why? Because if F is an isomorphism, G is also an isomorphism, then G inverse takes you from here to here, W to W1. Therefore, the composition, okay, takes you from W1 to W1. And that is identity. Okay. So G inverse F is identity, is same as saying G is F. Okay.
Hello, sir.
Yeah.
Sir, can you please repeat the proof?
Proof of this one, right?
Yes, sir.
Suppose you have two well-ordered sets, okay, which are isomorphic. Suppose there are two isomorphisms, F W1 to W2, G also W1 to W2. Now G is from here to here. You see, I will tell you what. Instead of repeating exactly the same way, then you will not follow exactly the same way. Let me say the following. We said an automorphism is identity map, right?
Yes,
and
sir.
Now, okay. I want to use this property. Okay. I have isomorphism between two different sets. I do not have automorphism. But I am determined to use what I know, this one. Therefore, how do I get automorphism? Okay. So the only way I get automorphism is I go from W1 to W2 and from W2 to W1. Right?
Yes, sir.
So if there are two isomorphisms, F W1 to W2, G W1 to W2, then G inverse goes from W2 to W1, right? G inverse.
Yes, sir.
Therefore, if you compose, okay, G inverse circle F, it is an automorphism of W2, not W1. This is a printing mistake. Wait a minute. Sorry, it is W1. G inverse circle F. Why? Because if you take any point in W1, you calculate Fx. Okay? You calculate G inverse of Fx. Okay? That is again a point in W1. And because F is order preserving, because G is order preserving, G inverse is order preserving, composition of two order preserving things is order preserving. Okay? Therefore, this is order preserving. And this is an automorphism. Okay? Because F takes you from W1 on to W2, G inverse takes you from W2 on to W1. Therefore, it is an automorphism. Is it okay?
Yes, sir.
So that's how, you see. A O set cannot be isomorphic to an initial segment of itself. Fantastic. Okay? Why? Because if you take an initial segment, let us say set of all points x less than u. Suppose W is isomorphic to this one. Then F is an ordered preserving map from W to this initial segment. In particular, F of u should be in this segment. That means F of u is less than u. No way. Okay? So you see? So beautiful. Well-ordered sets are extremely well behaved. They are not only well ordered, but they are well behaved. Okay? Now, here comes the main observation. We are heading to this. Suppose you give me two well-ordered sets. Exactly one of the following holds. There is an isomorphism of this to this, or there is an isomorphism of this to an initial segment of this, or there is an isomorphism of this to an initial segment of this. Okay. Now, there is no need for you to remember this nonsense. As I said many times, you keep on thinking two separate lines of people standing. Okay. The first fellow in each line is mapped. The second fellow in each line is mapped to each other. The third fellow is mapped, and so on. Okay. This way you continue. Either you end up mapping all of W1 to W2, or some points of W1 are left out, but W2 is finished. Or some point of W2 is left out, or W1 is finished. That's all. Okay? So, if there are two lines, then you can make a correspondence between the lines. Okay? Either it will be a correspondence between the full lines, or of one line to a segment of the another line. That's all. But I have used in my explanation and so on. Okay? Take the first element of W1, correspond to first element of W2. Take the next element of W1, next element makes sense because the first element complement has a least, that is the second element. Make it correspond to this and so on. Okay? And so on will now be avoided, and I will give you an indication of the proof. Okay? But I am going to say exactly the same thing. I have to define a function from W1 to W2. Okay? What I do is the following. Look at the set of all x comma y. X is in the first set W1, y is in the second set W2. Okay? So, you please imagine not abstract sets W1, W2, two bags. Okay? Two people standing in a line. Okay? Now, the set of all points x comma y such that W1x is isomorphic to W2y. If the segment here below x is isomorphic to a segment here below y, then I put xy here. Otherwise, I don't put. Okay. I want to convince you that this is a legitimate function and this gives you the answer. Okay. I will now see again. The proof is a little lengthy one. However, it is just like putting one step after another step and so on and so forth. Each step is very trivial. So first of all, is there any point x comma y at all satisfying this condition? Sure, because if you take the first point of W1, call it x, first point of W2, call it y, that point is here. Why? Because the segment determined by this initial segment is empty set. Initial segment determined by this is empty set. Both are empty sets. Okay. But of course, most of the time when we were students, we have trouble with empty sets. So you may not like empty sets. Okay. Then you can go to the second elements. Okay. And so on. And if you don't have second element, proof is complete. Don't worry. And if there is a second element in both, go to second elements and you can avoid talking about empty set. That is not a problem. Okay. The next thing is the following. Given a point x, can there be 2 points y1, y2? Okay. I am going to concentrate on this for you now. Okay. This is all written down, but I don't want to go down. You can look if you want. If you take a point x, can there be 2 y1, y2 such that x comma y1 is here and x comma y2 is also here? No way. Why? Because if x comma y1 is here, then w1x is isomorphic to w2 of y1. And if x comma y2 is also here, the same w1x is isomorphic to w2 comma y2. What is the upshot? w2 comma y1 and w2 comma y2 are isomorphic. That is the upshot. But impossible. Either y1 less than y2 or y2 less than y1. So in either case, you are going to show a well-ordered set which is isomorphic to an initial segment. Okay? No way. Similarly, can there be a y for which there are 2 x's here? That means, any question? No. x1 comma y is here, x2 comma y is here. No, because exactly the same reason. Let me repeat so that you understand. If x1 comma y is here, x2 comma y is here, then W1 of x1 is isomorphic to W2y. W1 of x2 is also isomorphic to W2y. Therefore, these are isomorphic. W1 of x1 and W1 of x2. But no way. One is an initial segment of the other. Okay? So, don't pay attention to symbols. Think of people standing in a line. Okay? You are comparing two lines, but then I am going to just one line. Okay? X1y, X2y are here. Then I come to this line and argue W1x1 and W1x2 are isomorphic. Okay. Therefore, for every x there is one y. Given x there cannot be two y's. Given y there cannot be two x's. Therefore, this is a function defined on somewhere. Where is it defined? Very simple. Suppose there is a point x comma y here. If you take any x prime less than x, that is also here. That means if you take x prime less than x, I can show you y prime so that x prime y prime is here. Okay. Why? Because if xy is here, there is an isomorphism between this and this. You told me x prime is less than x. Therefore, x prime is here. Therefore, this isomorphism takes that x prime to some y prime. Take that y prime. Okay. Now, I have used this isomorphism takes x prime to something. What do I mean by this isomorphism? There is only one isomorphism between two well-ordered sets. Therefore, okay, there is no choice for you. You don't have to ask me which isomorphism. There is only one isomorphism. Therefore, if x comma y is here, there is exactly one isomorphism. If x prime is less than x here, that isomorphism takes you to y prime. It is trivial to see x prime, y prime is here. Similarly, if y prime is here, if y is here, then y prime is also here for some x prime. Exactly the same argument. Xy is here. Take any y prime smaller than y. Then look at the isomorphism between W1x and W2y. Y prime is less than y. Therefore, there must be some x prime here which comes to that y prime. Take that x prime. Okay. And the order preserving nature tells you that that is an isomorphism between the initial segments. Okay. Therefore, if a point x is here, anything smaller than x also appears as a first coordinate. If a point y is here, any y prime less than y also appears as a first coordinate, the second coordinate. Therefore, now what I do is the following. Okay, I shall define V1, okay, denote these by V1 and V2 respectively. What is F is a graph of an ordered preserving map with domain union of initial segments of W1 and range union of initial segments of W2. Okay, that is what I argued so far. Denote this union of initial segments by V1 and this union of initial segments by V2. Therefore, F will define a map on V1 to V2. So where are we now? We are now a subset V1 of W1, a subset V2 of W2, and this is union of initial segments. This is union of initial segments, and F is a one-to-one map order preserving on this onto this. Okay. The question is, can we make this W1 or this W2? If I did, proof is over. Okay. Now, suppose you say no, this is not W1. If this is W1 and this is W2, proof is over. I have an order preserving map. Okay. Again, as I keep on telling, don't pay attention to VW nonsense, but initial segment, it is the words and the picture you have to pay attention. Okay. Union of initial segments. Okay. For example, if you take the integers 0, 1, 2, 3, 4, 5, etc. 0, 1, 2 is an initial segment. 0, 1, 2, 3 is an initial segment. 0, 1, 2, 3, 4 is an initial segment. All these make up the entire natural numbers. Okay. Therefore, it is quite possible this may make up all of W1. This may make up all of W2. Then you have an isomorphism from here to here. Okay. Please remember how this earlier beautiful observation that any isomorphism is unique is playing a crucial role. Okay, fantastic. Now, suppose you tell me, no, this is not W1, this is not W2. Okay, all right. Then how much can it differ from W1? How much can it differ from W2? Can there be 2 points not in V1? And can there be 2 points not in V2? No, there cannot be. Because if there are 2 points, then take the first point outside V1. That means look at W1 minus V1 and look at the least point there. Similarly, look at W2 minus V2, look at the least point there. The isomorphism between these two can be extended to those points. Okay. So that will lead to a contradiction. Okay. V1 is the union of all these things. That point x1 comma y1, if x1 is the first point outside V1, y1 is the first point outside V2 in W2, then extending your isomorphism from here to here to x1, y1 will put x1, y1 here. Okay, in the graph. Why? Because what I said, adding x1 to v1 is actually an initial segment determined by the next point. You said there are 2 points at least. Similarly, adding y1 to here is an initial segment of w2. Why? Because there is another point here you told me. It is a segment determined by the next point to y1. And this contradiction shows there cannot be 2 points here and 2 points here. So, both. So, either this is less than or equal to 1 or this is less than or equal to 1. Only one of them. I don't know. Okay. So, if this is less than or equal to 1.
Can you explain this again? Why can't we do more than
okay? Suppose V1 minus V1 has 2 points. Okay. Are you imagining W1 as a line of people standing? And V1 is all initial segments and cut off somewhere. And W1 is the entire line. So the remaining portion is the remaining people in the line, W1 minus V1. Similarly, W2 minus V2, remaining people in the remaining part of the line. Look at the first point in the remaining part of the line. Look at the first fellow in the remaining part of the line here. You can make a correspondence between these two. Is it okay? Suppose x1 is the first point outside V1, okay? And x2 is the next point after x1. Remember, when I say x1 is the first point outside V1, I mean least point of W1 minus V1. And x2 is the least point of W1 minus V1 and also minus x1. Okay, x1, x2. So the line W1 after V1 continues with x1, x2. Similarly, the line W2 after V2 continues with y1, y2. Now, I have an isomorphism from here to here. I can extend it. I will map x1 to y1. That will be an isomorphism of the initial segment V1 union x1 to V2 union x2. Why is V1 union x1 initial segment? It is determined by x2. Is it okay? So you have to get the mental picture. As long as you keep on looking at the symbols V1, V2, you will not get. Okay? Think of V1 as initial segment of a line of people standing. Think of V2 as the initial segment of the second line of people standing. You have established a correspondence up to this point. Now, what is left over in the two lines? Okay, that's it.
Hello, sir.
Yeah.
So are V1 and V2 initial segments?
Of course, union of initial segments.
So they are like the.
Wait. You see, as I said, it could be all of W1. Then the proof is complete. Okay?
Yes, sir.
You see, suppose V1, V2. V1 is union of initial segments. Okay? Union of initial segments is either an initial segment or the whole set. Is
Yes,
it
sir.
okay?
Yes,
Correct?
sir. So this is like the maximal initial segment.
Oh yeah. So V2 is also either an initial segment or the whole. Okay? If both are wholes, the proof is complete. If one of them is whole, the proof is complete. Agreed?
Yes, sir.
Therefore, let us assume that both are initial segments. Okay? If this is all of W1, the proof is complete. If this is all of W2, the proof is complete. We have a thing here, I shall mark it to this. Is it okay?
Yes, sir.
Think of people standing in line. Okay? Now,
Sir?
things are left over in both. How many can be left over? I said either 1 or 0 here. Or there may be many things left over here, either 1 or 0 here. Okay? I argued you cannot have 2 left over here and 2 left over here. Is it okay?
Sir, I have a question.
Sure.
Yeah, so the question is that can we say that we cannot have both? I mean, the cardinality, I don't know. The size of W1 minus V1 and size of W2 minus V2 cannot be the same. That's what you mean?
No. That is why I said don't confuse with everything you know. Okay. Now,
okay.
I know you are familiar with cardinality and number of points and so on, but you see, I keep on repeating the sentence again and again. When you think of well-ordered set, please think of people standing in a line.
Yes, sir.
Don't think of objects put in a bag. Okay?
No,
Is
sir.
it okay?
No, I mean, I'm trying to say that the same number of points can be left over in both the sides. So why should it be equal to 2? Let's say.
You see?
Why are we taking the number 2? Like.
No. I said you see, greater than or equal to cannot be left over. That's all. Okay, fine. All right. If you are bothered with that, let me argue differently. Okay. I know once a question arises, if I answer the question in exactly the same way I said earlier, you will probably get the same question exactly the same way. Okay? Therefore, let me use an argument like this. V1 is a union of initial segments of W1. V2 is union of initial segments of W2. Okay? Suppose this is all of W1. Then do you agree the proof is complete?
Yes, sir.
Yes. Suppose this is all of W2. Then you agree proof is complete? From here to here you have a map. Right? Therefore, assume.
Sir, I'm only worried about the number 2. Why just
No. Wait. Don't worry. That is why I said don't worry about anything. You see, mathematics is free of any worries. If there is any worry that is caused to you, somebody else is responsible. You don't worry about anything. Okay? Don't worry. Forget about that. Okay?
Okay, sir.
Forget about that.
Yeah.
Hello, sir.
which are not in V1. There are people in the line W2 which are not in V2. Look at the first fellow in the line left over here. Look at the first fellow in the line left over here. Okay? Because these are well-ordered sets, remember. Okay? They are not objects put in a bag. Make the correspondence between the first point here and the first point. Therefore, you have got V1 union X1, V2 union X2. You have an order preserving map. Is it okay?
Yes, sir.
Very good. If this is W1, if this is W2, it is over. You agree?
Yes, sir.
Okay, good. Suppose you say, no, sir, this is not W1. After X1, there is still one more fellow X2 here. Okay? Agreed?
Yes, sir.
And after Y1, there is one more fellow Y2 here. Okay? Then I say, come on. That cannot happen. Why? Because if there is a fellow X2 still here, if there is a fellow Y2 still here, look at the initial segment determined by X2. Okay? And look at the initial segment determined by Y2. Then X2, Y2 should be in your gap, right? Because the initial segment determined by X2 is V1 union X1. Initial segment determined by Y2 is V2 union Y1. They are isomorphic. Okay? So.
Hello, sir.
Yeah.
Sir, do you mean to say that X1 should be in V1 and X2 should be in V2?
Naturally. If there are 2 points left over here, let us say, at least 2. You see, now Bhashan is worried about 2. That is why I want to avoid 2. I want to come down from below.
Hey,
Goofy.
Hello, sir.
Yeah.
So basically, this contradicts the maximality of V1 and V2.
Right. I have taken, there is no max. Yeah, I took F. Okay. Looked at the class of all, left with the set of all XY satisfying that condition. Okay. Now, if nothing is left over here or nothing is left over here, proof is complete. Suppose something is left over here, okay, and something is left over here. If there is only 1 point left over here, then also proof is complete, because I will extend this isomorphism to the last 2 fellows of the line. That is an isomorphism from W1 to W2. Okay? If there is only 1 fellow left over here and many left over here, even then proof is over, because I will extend the isomorphism from here to here. So W1 is isomorphic to an initial segment here. I don't care how many are left over. If there is only 1 left over here, many left over here, even then the proof is complete. Okay. Therefore, proof is complete if nothing is left over in both. Proof is complete if just 1 is left over somewhere. Now, suppose more than 1 is left over. Okay. Then I am saying that cannot happen, because if more than 1 is left over here, let us say X1 is the next point, X2 is the next point, and many others are there. I don't care. Let us not use the word 2. Okay. More than 1 is left over here. I don't know how many. Let us say Y1, next point, Y2. Okay. Then look at X2, Y2. Okay. So the initial segment determined by X2, Y2, they are isomorphic. Where is that? I don't know. Yeah, correct. The initial segments, okay, X1, X2, Y1, Y2. If you look at X2, Y2, that should be in F, because the initial segment WX2 includes V1 and X1. Initial segment here, Y2, that includes V2 and Y1. Okay. Therefore, in either case, there is a contradiction. That should have already been here. Okay. Now, I would like you to think about it, but you don't have to accept anything. Okay? There are some things which, if somebody explains, it may become complicated, but if you think, you say, oh my God, this is very trivial. Okay? So you think about it, you can ask me. There's no problem. Is it okay?
Yes, sir.
Yeah, so think about it. So, and that's all what I have written here. So, between any two well-ordered sets, you can compare. Okay? This stands to reason. If two lines are there, people standing in two lines, you can compare the lines, right? One by one, people. That's it. There's nothing profound here. But the word so on is avoided. That is what we should carefully see. Okay. Now here comes, I told you that I am going to make precise your this kind of thought process. Okay. This kind of thought process. Okay. And now I am making it precise. I would define a set is said to be transitive if whenever there is a point in the set y, and if x is a point in y, then x also must be in A. Okay. So if you have a set, if we have a point y which is in the set, and if there is a point x in this set, then x also should belong to A. Such a set is called a transitive set. Okay, transitive, as the name implies, belongs. You know, remember I told you transitive relation: A less than B, B less than C, then A is less than C. Exactly the same thing. X epsilon y, y epsilon A, x epsilon A. Okay, x belongs to y belongs to A, then x belongs to A. This may look very peculiar to you because we are not used to this kind of notion. I will give you plenty of examples. Maybe before you get confused, let me already start giving examples. Okay? Then you would know. Right. Empty set. Please ignore the word ordinal. Empty set is a transitive set. Why? If there is anything in this, well, there is nothing. You don't have to verify. The set consisting of empty set is a transitive set. Why? Suppose something is in this set, yeah, empty set is here. Is there anything in that? Nothing. So you don't have to verify. Very good. The set consisting of empty set and this one. This is a set which has 2 points, this and this. Okay? This is a transitive set. Why? What belongs to this or this? Okay? All right, let us take this as y. Is there anything in this? No. So nothing to verify. Very good. So let us take this. Is there anything here? Yes. This one, empty set. Is it in my set? Yes, it is here. Similarly, you can now think of set consisting of empty set, this and then this one. So I would like you to think of these things. These are transitive sets. You can build transitive sets, okay? And incidentally, that is precisely what I am making precise. Somebody already commented, you know, you can think of n after 0, 1 to n. So I am thinking of everything as the previous things. Anyway, let me not explain too much. So I hope you are convinced that this is a transitive set. I hope you are convinced that the set consisting of this, that's a transitive set. I hope you are convinced that the set consisting of these two things is a transitive set. Now, of course, you can, if you are convinced, okay, many times we nod our head without getting convinced. That leads to problems. But if you nod your head only after you get convinced, that won't lead to problems. You can discover by yourself. Now, look at the set consisting of 3 things. This, and this. That is a transitive set. Okay? All right. So, a set is transitive if whenever x is in y, y is in a, then x is in a. Point of a point is here. And you see, many times we are used to writing 1, 2, 3 as we have learned in elementary school. They don't look like sets. Okay? They look like some pictures. How come what belongs to this picture 1 that you write? Okay? So that is why there is a problem. But if you remove that mental problem, then, okay. An ordinal number is a transitive set which is linearly ordered by this. Okay. An ordinal number is a transitive set. That means if something is there, y, and some other thing belongs to this y, then that also should be in your set. And this should be linearly ordered. That means if there are two things, one of them belongs to the other. Okay. So that is called an ordinal number. I will give you many examples. I have already given you, but I will show you once again so that you will have time to think about it. The adjective, yeah.
Sir, can you also say it's ordered by inclusion?
Sure, it is ordered by
inclusion.
Linearly ordered.
Hello, sir?
Yeah, right.
No.
But if it is simply linearly ordered by inclusion, that is not good enough. Okay?
Okay, sir.
Suppose I take the set consisting of 1, 2, and the set consisting of 1. Okay? And the set consisting of only these two. 1 and 1, 2. That won't be ordinal because it is not transitive. You see?
Okay, sir.
Yeah. So carefully think about it. Now, I have used the word number. You may get worried, what the hell is number? Well, you know natural number, you know rational number, you know real number, and this ordinal number is also exactly like that. Okay? But it extends the concept of number, natural number, in the counting direction, as opposed to in the direction of groups and fields. When you go to rationals, reals, you have gone in the direction of groups and fields. But I am extending in the direction of counting. First, second, third, fourth, fifth. And then at the end, there is one more fellow standing, infinitieth. At the end, one more fellow after him, infinity plus, and so on. Okay. So, an ordinal number as of now is simply a transitive set which is linearly ordered by this belonging to. Okay. That means what again? Please remember. Of any 2 points in your set, one should be an element of the other. Okay. And this definition of ordinal numbers were introduced by Cantor, but this definition is due to von Neumann. Okay. Now don't pay any attention to the regularity and so on at this moment. Okay. Now, I want you to carefully understand, because the concept of transitive set, the concept of linear order are involved, you may get confused because we are now coming to the heart of set theory in a sense. In set theory, everything's are sets. And in real life, sets are pictures. Okay? You think of the set of all chairs. You think of the set of all people. You think of the set consisting of the picture 1, picture 2, picture 3. I don't know whether you write in English or Hindi, whatever, numerals. You think of that. But you never think of anything belonging to 2, anything belonging to 1. 1 by itself is a full object for you. Okay? Therefore, we have come to real heart of set theory, and you have to be very attentive here. Okay? Empty set is a set. I say that is an ordinal. It is transitive. Sure. And linearly ordered. Yes. And this set consisting, by the way, I will denote this by 0. Okay?
So may I ask a question?
Yeah.
Are all transitive sets constructed like this?
All like what?
Like what you said, a 5, and then the set containing 5, and the set containing 5, and the set containing 5.
There are very, very transitive sets.
No.
Okay. There are transitive sets which are not ordinals. Okay?
Okay,
yeah.
thank you.
So, you see, ordinal, okay, good. So, it is like this. I kept on telling you, partial order is like a crowd. Linear order is like a line of people, correct? Okay. Now, I will tell you, transitive sets are like cones. Okay? A cone. Remember? A cone, there is a vertex, right? And if you go along any ray, everything below that is in your cone. Okay.
Mhm.
So you can think of a partially ordered set as a crowd, a linearly ordered set as a line, and you can think of transitive sets as cones. Mental picture. Okay, please don't confuse with your functional analysis cone. Okay, there is no functional analysis here. Only mental picture. Okay?
Right. Thanks.
Yeah. Okay. And there are many transitive sets. Okay.
So can you give an example which is not an ordinal?
Oh, yeah, sure. Why not? Yeah, sure. Yeah. Now, there will be many models of set theory, okay, which contain things that are not ordinals. Okay. For example, suppose I take the power set of this and so on. Okay. Power set of this along with these things. Okay. You can cook up many things, many transitive sets, which are not ordinals. Okay. All right. Maybe I will specifically write down one for you next time.
Okay.
Okay. If you want to see in black and white. Okay. I know no matter how much I say, the word is in the air, it flies. But if I write on paper, you see. So I will do that next time. Okay. Plenty.
Yes, sir. Thank you.
Yeah. Okay. And the set consisting of empty. No, this is an ordinal. As I already explained, this is transitive and it is linearly ordered by epsilon. There is only one thing here, nothing to worry. This is transitive.
Hello, sir.
Yeah.
So
Okay.
can I ask a doubt? Like in old set theory, natural numbers are just defined as a set of symbols that satisfy 5 properties, right?
Yeah.
So like the advantage of actually defining natural numbers like this is it that you can have ordering and counting.
Yes, you can have number one, you can have ordering. Number two, you only use empty set. That is the only symbol you are using, nothing else. Okay.
Yeah, is it like both counting and ordering come with the structure, but in the old set theory, you have to develop ordering later on, right?
Sure, definitely. Yeah. Okay. Now, at this point, let me tell you, you might think things are getting very complicated, but they are not very complicated. Yesterday, I gave you the analogy of color. If somebody tells you about colors right at the beginning, as a frequency of waves and so on, like rays, you won't understand. Now, let me tell you, it goes to the credit of all our elementary school teachers and our parents that they have taught us numbers 1, 2, 3, 4, 5. We are extremely comfortable with numbers. Okay. But let me tell you, we know nothing about numbers. We know nothing. Why? Because suppose somebody asks you what is 1. Have you ever seen 1? Have you ever seen 2? There is no 1, there is no 2 anywhere. Okay. You say, no, I have written the symbol 1 in English language. But I write the symbol 1 in Telugu language. And Krishna writes in Hindi. Somebody writes in Sanskrit. So what is that 1? So that means what you write as symbol, English, numeral, is an illusion. It is only a symbol. So 1 we have not seen. Then 1 apple you have seen. 2 apples you have seen. Okay? You see? So have you seen apple? No, you have not seen apple. Where is apple? You have seen only examples of apples. You see, most of the things in life are abstract. But nobody ever made us feel they are abstract. They are concrete. Okay? Nobody told us what exactly is an apple. And in fact, if you remember, when you were children, you would keep on asking your dads, oh, what is that? What is this? What is that? And so on. And then at some stage, they get fed up and say, shut up. Things are all abstract. So 1, 2, 3, 4 that we write in pictures, okay, are just an illusion. We have made a mental picture of those things. And depending on your language and culture, you make your own mental picture. But remember, whatever is your culture, whatever is your language, 0, 1, 2, 3, etc. have a universal significance. Okay. So that is precisely what we are trying to do here. This is 0. We denote by empty set. This is 1. This is 2. Okay. Advantage is we use only one symbol. We don't use many pictures. Okay, now please extend your imagination. If you look at the set consisting of this, this, and this, a set which has three things in it. This is one thing, this is the second thing, and this is the third thing. That set, okay, is three. And the set consisting of this, this, and the one I just now described, those four things, that will be four, and so on. Okay? Now, what are you doing here? Whatever so far the set you have, you collect all those things, add that set at the end. Okay? So, these are all ordinals. If alpha is an ordinal, then beta, which is alpha union, the set consisting of alpha, this is an ordinal. This will be denoted by alpha plus 1. Okay? Now, here I said, when I gave you the examples, okay, 1, 2, 3, and so on. Oh, I don't know where I put. Anyway, doesn't matter. Okay, doesn't matter. Okay, earlier I have written 0, 1, 2, 3, 4, infinity, infinity plus 1, etc. I went to the right side. Now, if somebody is a left-handed person, he would be writing 0, 1, 2 this side. Okay. Therefore, a line forward, backward, they have no meaning at all. It depends on how you look at it. Okay. Therefore, here is the definition: ordinal, which does not depend on the words, so on and so forth. On the words, go right, go left at the end, blah, blah. A transitive, linearly ordered under epsilon set is called ordinal. And each ordinal is a well-ordered set. And why is it well-ordered? Because under belonging to, okay, there is an axiom in set theory, which is called the regularity axiom. If you take any set, then under this relation, there is a least element. That means if you take any set X, there is a Y in X, so that there is nothing else, okay, which belongs to Y in your set. This is called regularity axiom. But don't look at the symbols, useless. So remember in words, regularity axiom says any set has an element which is the least in terms of epsilon. That is, there is a point in your set, X, which is in your set, and there is no Y in your set which belongs to X. Okay? And that is why ordinals are well-ordered sets. If you have an ordinal alpha, then alpha union, the set consisting of alpha is an ordinal. Okay?
But
hello, sir.
May I ask a doubt? I mean,
sure.
Empty set is there, and so
Yeah.
all sets have this regularity property. I mean, all classes.
Empty set? Yeah, sure.
Right.
So
why is it? I mean, it's an obvious axiom in the sense that.
No, it is not an obvious axiom.
No.
They have not taken it as an axiom earlier. Okay?
Oh, okay.
Then somebody asked the question, can X belong to X? Okay. Can X belong to X? They said, yeah, they can. Then Van Neumann came along and said, it is a very funny situation if X belongs to X. Okay?
Okay.
Therefore, let us make this axiom. And he showed this axiom is consistent, by the way. Okay? They have taken axioms of set theory without this regularity to start with.
Okay.
And Van Neumann said, don't worry, if you like this axiom, take it. There is no contradiction. Okay?
Okay, thank you.
That is very good.
Hello, sir.
Yeah.
Can you please repeat that? Like you said something about minimality, right, in that axiom?
If you take, so in set theory, everything is a set. There are no pictures. Okay? The 1, 2, 3, etc. you are thinking of in pictures. They have no role to play. We have to define everything in terms of sets. 1 is a set, 2 is a set, 3 is a set. Everything is a set. There is nothing more than set. Okay? Just as in a group, there are only elements of the group. Okay? In sets, in the models for set theory, in theory of sets, there are only sets, nothing else. Okay? Chain is not an element of this thing. But in practice, we think of the set of chairs and so on and so forth. Okay. Now, what did I say?
Sir,
Yeah.
I would like to remind you that you have 10 more minutes.
Okay, fine. Yeah, I'll stop in a couple of minutes. Yeah. Yeah. You see, if you take a now, let us see. So I would like you to understand carefully how we have all been brainwashed into believing that we know everything we say. The symbol 1, the symbol 2, the color red. Okay? You see, when you were small, probably you asked your dad, showing a hut, is it a house? Showing a big building, is it a house? How come both are houses? Then your father had no answer. Okay, shut up. You see, so many things we learned like that. Absolutely, we have no idea at all. Okay, if a small child comes and asks, is this a table? We say yes. What is a table? Silence. You can say 4 legs, but then if the child asks, if there are 3 legs, is it not a table? You see, so there is tremendous problem there. Okay, and it goes to the credit of our teachers that they have been able to instill a sense of confidence in using all those things. But now we are making things precise. Okay, so if alpha is an ordinal, then alpha union singleton alpha is also an ordinal. I will continue from here next time, and what more I have to do in ordinals is simply describe to you some properties of ordinals, then I will connect them to cardinal numbers. Okay, and then I go back to that axiom of choice and transfinite induction. This I shall do next time. But Haimanti is going to talk to you about cardinal numbers, and there are some cardinal numbers among these ordinals also, which we shall specialize next time. That is what we shall do. Now, there is 5 minutes left. Since there are too many questions, I will stop in the 5 minutes. And I stopped sharing, so you can. Yeah. Okay. Now, I need moderators' help.
Sir,
ask any question from there, because there is
so discussion kind of went off the topic for some time. Yeah. So I request the participant to ask the questions directly now, or they can retype the questions again so that it's easier for the speaker.
Sir, can I ask a question?
Yeah.
So yesterday you said something about these axioms not always being consistent.
No.
Okay.
What I said is the following. Okay. Is there a sigma ultra filter that extends the co-countable filter? Okay. Now, that you cannot prove there is such an ultra filter in set theory. Suppose you take the statement, there exists a sigma ultra filter extending co-countable filter on the real line or whatever. Okay. Not real line. Is there any set, and is there a co-countable ultra filter? Sorry, is there an ultra filter on that set which includes the co-countable filter? Okay. Now, you cannot prove it. Next question. If you cannot prove it, whether the statement there exists such a thing, is it consistent? Like CH is consistent, AC is consistent. Can you show it is consistent? No, you cannot show. That is what I said. Is it okay?
Yes, sir. That is what I meant by you saying. Yeah, those axioms are not.
Yeah. So you cannot show it is consistent. You see, there is a level of statements which you can prove in ZF. Okay? And there are some statements which you cannot prove in ZF, but you can show that no contradiction is arrived by using that axiom. like axiom of choice and continuum hypothesis. That's the next level, which you cannot prove, but you can show they don't lead to contradiction. And there is another level of statements where you cannot prove them, you cannot show that they are consistent. Okay? You cannot even do that. So this belongs to that level. That's all. Yeah.
Okay. Thank you.
Hello, sir.
Yeah.
Sir, so the empty set, so in this language of ZF, do we take empty set as a constant symbol, or is the existence of empty set guaranteed by some axiom of ZF?
No, there's an axiom. Oh, I have not mentioned axioms of set theory. So as I said, set theory is a theory. That means it has a language and it has axioms. And for example, let me tell you, just to give you an idea, okay? There exists a set which does not contain anything. That's an axiom. That is denoted by empty set, okay? Whether you want to denote it by phi or a duck or a chain, it is up to you, okay? But that is called empty set. Okay?
Hello, sir.
If there is a set X, if there is a set Y, then there is another set which contains exactly these two, X and Y. That is another axiom. In this way, there are several axioms. Okay? Yeah, so empty set is an axiom.
So doesn't it happen that the axiom of regularity that we have, so the set phi satisfies in the sense that instead of we have the axiom of regularity as for all x, there exists some set y such that something happens. So the empty set
correct.
The y property for y. So sir, why is it taken? Why is the regularity axiom taken as a separate axiom and not why isn't it a?
Because as I said during
the empty set satisfies that.
What? Of course, empty set satisfies that. Are you saying that empty set belongs to empty set?
Is the axiom of regularity?
Wait. Are you saying empty set belongs to empty set? No. Nothing belongs to empty set.
Okay, yes, sorry, yes.
Nothing belongs to empty set.
Yes,
no problem. Absolutely. Yeah.
Hello, sir.
Yeah.
Sir, in some textbooks, they actually mention this axiom of the empty set, existence of the empty set. But in some textbooks, they actually derive it using the second axiom of like ZF2.
What is
like that? That is for every every set, there is precisely a set which contains all subsets that satisfy A of X, some condition on X.
That's okay.
So you can take A of X to be X not equal to X, and then you can prove the existence of the empty set.
How do you know that there is a set which satisfies this condition, X not equal to X?
No, that is actually an axiom.
Which is an axiom?
That is for any given set Y, there is precisely one set that contains set of all X and Y such that A of X.
Yeah.
For any given condition on X.
I see. Okay, fine. Sure, you can do that. That's no problem. This is called selection scheme. Okay. Yes, you are right. If you have a formula phi x, okay, and if you have a set y, then all x in y which satisfy phi x is a set. Okay.
So my doubt was why do some authors introduce that as an axiom, and why do some authors prefer deriving it as a consequence?
It is nice to have it. You see, that's all.
Okay, sir.
Because you see, for example. You see, suppose somebody defines groups, okay? Then he says that there should be an identity element and so on and so forth. We want it to be non-empty, that's all. Okay?
Yes, sir.
Some people define group without this, there exists E kind of thing also. Okay?
Yes, sir.
You can do that. So is empty set a group? So if you don't say that there is at least one thing, then I can say, okay, there is nothing. This is a model for set theory. Do you accept it? Suppose there's nothing. Nothing. That's a model for set theory. Because all axioms will be satisfied. If there is nothing, all axioms are satisfied, right?
Yes, sir.
So something is there, you see. So that's all. So it is just for psychological reasons. It is better to say empty set is there. Otherwise, you can always take a model of ZF. There is nothing. That's all.
Okay, sir.
Yeah. Okay. Sure.
Hello, sir.
Hmm.
Sir?
Yeah, sure.
Sir, this is with regard to the question I asked earlier this morning, the definition of posset.
Yeah.
So I understood the perspective which you said. They are two they are two different languages and they are translated. See,
Yeah.
but for example, if you take the definition of lattice, so one you have as a pure algebraic object with meet and join operations satisfying certain axioms. So this is one way of looking at a lattice. The other way is with a order and satisfying certain things.
Correct.
So the translation which you said is in this sense, the same object lattice, you are looking at this as an algebraic object wherein you don't have any discussion of order, but then the other thing you look at it in terms of an order, like a partial order. But in our case, posset, both the things have a relation. Less than or equal to.
Right.
So you forget the symbol less than denoted by delta. So suppose if someone say you have a set W and I'm defining the relation delta.
Yeah.
So should I, and if they ask me to verify if it is a posset or not,
wait, hold on. If they ask you to verify whether it is a posset, right?
Yes.
Who are they to ask you? Did they tell you what is a posset according to them? Did they tell you what is a posset according to them? Ask them. If somebody asks you, verify this is a posset, then you ask them, what do you mean by posset? Tell me, I will verify. You see? Sure, you should ask them.
Okay.
Okay? I mean, they don't have one definition and you have one definition and you see? So if somebody asks you, verify this is a posset, then you ask, okay, what is your definition of posset? Tell me, I will verify those things. Okay?
Okay. No, so if I have a set and if I want to define a posset, a posset structure, so both these two definitions, there is reflexity in one, anti-reflexity in the other. So yeah, this is my confusion. You have a relation. In one definition, you are looking at reflexity. In the other definition, you are looking at anti-reflexity.
Wait. You see, I am looking at one symbol, okay, less than another symbol, which includes equality also. Okay?
Yes.
So, there is no contradiction at all. Why confusion? It is for you to decide what you would like to follow. Right?
Okay.
It is for you to decide what you would like to follow. Okay? Whether you want to follow less than, do it. If you want to follow less than or equal to, do it. There is absolutely no confusion at all. You see?
Okay.
Yeah. No. It is for you to follow. Okay?
Okay, sir.
And because in life, sometimes we would like to talk about less than, sometimes we would like to talk about less than or equal to, it is better to know both. And it is also equally important not to get confused.
Okay, yes, sir.
Okay, that's all. Yeah. If somebody asks you to verify, ask them what is your definition, then I will verify. There are two definitions, so whichever you are following, tell me.
Okay, yeah.
Yes.
Okay, sir, I think it's already time. So I'm sure there are more questions, so we can reserve them for the tutorials afternoon.
Yeah, sure.
Yeah, so let me thank the speaker. Thank you so much, sir.
Thank you.
So hope that we'll see more examples and problems in the tutorial session as well. Thank you, sir. So we'll break for 10 minutes and then the next lecture starts at 11:45. Okay.
Thank you.
हेलो हाँ बोल हाँ आ गया Hello.
Hello, sir.
Yeah.
Yeah, so we'll wait for 1 more minute and then
Yeah,
start.
sure.
Yeah.
The previous lecture was longer, so we should wait.
Yeah, sure.
Participants should have some tea, coffee if they wish. Although we can't provide them with that.
Exactly.
So what are you doing?
So I'm in my 4th year of PhD.
Okay. Maths?
Yes.
Okay. Which
So
subject?
I'm working under Nikita, ma'am.
Okay.
Yeah. So it's on symbolic dynamics. So actually, I submitted my thesis this month.
Okay, good. So now waiting for the defense.
Yes. Waiting for the reports to come.
Yeah. Have you studied set theory before or?
Not as a set theory, but I have, yeah.
Okay.
Should we start now? It's 11:45 or wait for some time?
Yeah, we can start. I wanted to make some announcements, so that's why I was waiting if more participants want to join. But anyway,
So
we can.
I'll announce the lecture and then you'll announce. You'll do your announcements.
Sure.
Yeah. Okay. So probably then I'll do it.
Yeah, sure.
So hello everyone. Let's start the second lecture for today. So I welcome Dr. Amit Kupe for continuing his lecture on completeness and compactness theorems in propositional and predicate logic. So handing over to you, sir.
Thanks a lot. So yesterday there were a few questions about references. Yeah, so here are some references. I'm flashing them on the screen, and there is one more book which I will add in the chat. Yeah, which Professor Sujata Ghosh suggested yesterday. So that is by Enderton. Yeah, so these are some good books in logic if you wish to read something from them. Yeah, there are different aspects covered in different books, but these are all well-known books in this field. So there was some question yesterday, yeah, when I said something about the structure part and R to the 0. Yes, I can do that. Yes, Pratik, I will do that. So the structure part, yeah. So here I said R to the 0, and just now you saw what is 0. Yeah, everybody saw 0 is the empty set. And whenever you write the notation A to the B, then actually you are referring to the collection of all sets from B to A. Okay, the collection of all functions from B to A. So R to the 0 is the collection of all functions from the empty set to real numbers. So before we say anything about how many elements are there in this set, let us recall that a function is nothing but a triple. Yeah, it is a triple of set A, B, the domain, the codomain, and a graph. Yeah, a graph of a function from A to B. So this triple denotes a function. So in this case, the empty set is the domain, then R is the codomain, and empty set cross R, yeah, that is the empty set again. And you need to take a subset of it which satisfies the function property that for every element of the domain there exists a unique element of the codomain. Now, because there are no elements in the domain, it vacuously satisfies, the empty set itself vacuously satisfies the property of being the graph of a function. And that is the unique function that we are talking about. Like after today's set theory lecture, you have a better understanding of this thing. And that is what I call by a singleton. If there are any questions, please do ask me. Yes, Ramakrishnan?
Yeah. Hi. So in your notes, the place where you've defined Boolean structure, Boolean algebra.
Right.
So just a small doubt. Should commutativity of the two operations be also there, or?
Commutativity, yeah, I mean, yes,
Yeah,
that should also be there. Yeah, this is not the entire definition. That is quite long.
Yeah, I mean,
yes,
exactly.
I'm missing some properties. Yeah, sorry for that. Any other questions about this R to the 0? Okay, so I will take it as a no. Right. So yesterday we defined what is a tautology, what is a tautologous set. It is a subset of all the it is a subset of the set of all tautologies. Then a set is satisfiable if there exists some valuation v for which vs is equal to true, which means all the formulas in that set get valuation true. And a set is unsatisfiable if there exists no valuation for which all the formulas in that set are true. Yeah, these are just different ways of doing same thing. Then we looked at the notion of logical consequence and some important properties. Yeah, so this exercise part A is the most important one. I will say we'll look at the proof theoretic version of that today. So S is a subset of SL and T and U are two propositional formulas. Then you can transfer this T from the left hand side to the right hand side of this double turnstile symbol, of the model symbol. Yes. Okay. Right. So, and whenever you have finitely many formulas on the left hand side, then you can combine them in the form of their conjunction. Yeah. And I mean, here I'm just talking about two, but if there were T1, T2, T3, then commutativity and associativity together allow us to say that, yeah, we can define. So for any finite subset of the set of formulas, the notation big conjunction of S is nothing but T1 conjunction T2 conjunction T3 up to conjunction Tk, where K is the number, like Tk is this is the entire set. And there is no confusion about parenthesis because of associativity of conjunction up to logical equivalence. Yeah. So similarly, disjunction is defined, and something more specific, that the disjunction of an empty set of propositional formulas is a contradiction, whereas the conjunction of an empty set is a tautology. So in order to see why this is true, yeah, this is generally counterintuitive if you are looking at it for the first time. So as there are more and more elements in this set S, as there are more and more formulas, then it is a stronger statement. And therefore you will have more logical consequences. Yeah, I mean, it could also happen that this conjunction is the bottom element. Yeah, I mean, it is a contradiction. But when there is nothing, there are no restrictions. Like conjunction is like putting more restrictions. When there are no restrictions, empty set of restrictions, then that is a tautology. And similarly, like the dual version is this. Right? Okay. Another thing which I would like to remind you is that when you draw the picture of a Boolean, yeah.
Can we relate which you said that if this is tautology, can we relate it to being the union at the intersection of phi being an whole universal space? Can we relate it to that?
Okay, so just now you were learning about set theory. Yeah, there is nothing like a universal space. If okay, one more thing you can do, that you can look inside the power set of a fixed set. Yeah, there you can see the analogy. There it is the top element. It is the full set.
Yes, sir.
Yeah, yeah, exactly this in similar way. Correct. Yeah, but there is nothing like a universal set. Yeah, set theory has to be defined in a precise way as a theory, a collection, a language, and a collection of axioms, which we will do. Yeah, I think tomorrow we will see that. Okay, so in a finite Boolean algebra, if you visualize it as a Hasse diagram, I mean, let us say the power set, then what are the elements just above the empty set? Can anybody answer that?
And the set of the set which contains empty set.
The set which contains empty
Singletons.
set, yeah, singletons, yes, yeah, singletons. I mean, your idea was correct that it will contain exactly one element. So these are all singletons. Just above the empty set, there are all singletons. Now the question is, how do you write any given subset using these singletons? It is simply the union. Yeah, we are just talking about a finite version here. So basically, every single element of, every single subset of a given set, of a given finite set, is a finitary union of singletons. We are going to generalize this here in propositional logic now. How will we do it? So we'll define a literal to be a propositional formula, which is either of the form P for a propositional variable or negation P. That's all. And the ones which will play the formulas, propositional formulas, which will play role of the atoms, yeah, when our language is finite, they will look like this. This big conjunction of pi to the sigma I, yeah, where sigma i's are either 1 or -1, depending on your choice. So you had to make a choice every time. So if it is p1, p2, pn, then you can say negation p1, conjunction p2, conjunction up to conjunction pn. Or you can say that, okay, I will choose first k to be negations, the rest k to be not negations. So these are the atoms. These propositional formulas play the role of singletons in the Boolean algebra of formulas up to congruence. Okay, and what is the result then? It is exactly what I said here, that if you have a finite Boolean algebra, finite power set, then every element is a union of singletons. So every formula is in the disjunctive normal form, which means it is disjunction of conjunction of literals. Okay, this is some standard form for formulas. And in order to convert any given formula into this standard form, what we do, we use these standard logical consequences, standard logical equivalences that we have here. Where do we have them? Yeah, here. Yeah, these are some of the standard logical equivalences. So we can use them. And why logical equivalences? Because you have this theorem here, which states that given any language L and a propositional formula P, there is a formula S in the disjunctive normal form, which is logically equivalent to T. So the main advantage of working with formulas in DNF is that we have some control over what that formula looks like. Yeah, that's all. So P if and only if Q, for example, can be written as P conjunction Q as one of the atoms, one of the conjunction of literals, and negation P and negation Q as the other conjunction of literals, and then disjunction in between. Okay, so this, any questions?
Yes, sir. I have a question. This sigma I, it's a car IC. So, what
So
do we
that
mean
is
by
just
the
a
car?
notation. That is just a notation. Yeah, Pi to the 1 is just Pi, and Pi to the -1 is negation Pi.
Thank you, sir.
Yeah, any other questions? Your voice is not clear. Whoever is talking, your voice is not clear to me.
That was my question. I'm clear right now.
Okay, thanks. Ramakrishnan, do you have another question, or is it the previous raise?
Sorry, it's the previous, I think.
Okay.
So I have a question.
Yeah.
Yeah, so this are of the form I equal to 1 to n, that could be any k less than n, right? Because we, or does it
I
have
is equal to 1 to n, where the language consists of only n propositional variables.
So is it necessary to have all the n variables? It could be.
Yes, it is necessary. I mean, if L is finite, then the atoms are precisely this. Whereas in the disjunctive normal form, that is not necessary.
Okay.
Yeah, I mean, this statement is precise. I'm not giving you the exact statement. The proof is also long. You can read it in one of the references.
Okay.
I just wanted to give you some idea that there are some standard ways of writing propositional formulas. And DNF is one of them. There is CNF as well, conjunctive normal form, where you write conjunction, then disjunction of literals. Yeah, it depends on your choice and what is the need.
Okay.
The application.
Okay, thank you.
Any other questions?
Excuse me, sir.
Yeah.
This is not a very concrete question. Just I wanted to verify an observation here. Would I be correct in saying that this last theorem, the thing about DNF, that corresponds exactly to the idea that we have of truth tables in propositional logic? That
the idea that we have of
truth tables in propositional logic, that we are doing disjunctions over each term in the disjunction corresponds to each row in the truth table that we have, or
truth tables can be drawn for, like, even for P if and only if Q. Yeah, by implies Q, you can draw a column. Yeah, you have a column for that. So that is not necessarily true. We are taking the minimal things. See here, like when there are only two symbols in your language, propositional variables in your language, then P and Q will make you are making a choice for that. So that this statement is true if and only if you have assigned truth values to P and Q in such a way that this is true and this is true. This will be true, this part will be true if and only if negation P is true and negation Q is false. So actually these atoms for finite language L, they will decide a valuation.
Okay, sir.
So each valuation, yeah, so P is given value true, Q is given value true. So that is a valuation because of our earlier result, yeah, that it could be any arbitrary function from the set of variables to truth values.
Yes, sir.
Similarly here. Yeah, so this is disjunction over different valuations which make that formula true.
Yes, sir.
Right. So there is one more thing that I haven't written down here because I want to reserve it for the tutorial session tomorrow. That is a set of connectives, an adequate set of connectives. So I just want you to think about this, that if you are given only the symbols disjunction and negation, then also you can write down every single formula. Yeah, you have access to all the truth tables. Yeah, like you are not allowed to use conjunction. but you are allowed to use disjunction instead together with negation, then you can do it. And similar statement also holds for implication. So implication and negation is also an adequate set of formulas. You can write down every single formula you want to say with the help of these two symbols. I will make the statement precise tomorrow. But for now, I just want to use that it is an adequate set of formulas and go to the next part. So let us look at this propositional logic, deductive calculus. And what is our motivating question now? So we are given a logical consequence T of a set capital S of propositional formulas. So let me remind you what this means. It means that whenever a valuation V makes all formulas in capital S true, then that valuation also makes all this formula T true. So there seems to be some kind of causal effect. Yeah, it depends, like this formula T can be somehow generated from formulas present in S. Now, how exactly can we say that? I mean, is there a way of logically inferring, purely syntactic, purely mechanical, algorithmic way to decide if this happens? Now, one problem with this, although mathematicians are quite used to it, is that you have to verify this statement for all valuations. Yeah, you pick a valuation, then check whether capital S gets value true, like everything in capital S gets value true, and then you verify whether T also gets value true in that situation. So if at all our language is infinite, then our job is actually infinite, correct? But then now we are asking whether there is an algorithmic, a purely syntactic way to decide this. Now, Professor Rao said something in the morning that every formula is finite. Yeah? Every formula has finite length. We classified SL into different fragments. Yeah, S0L, S1L, how many connectives we are applying. And that number of connectives that we apply is also finite. Okay, so that finiteness is important. So T, if you consider a single propositional formula, then how many propositional variables can it contain? Only finitely many. And then we should only be looking at the corresponding formulas in S. If it contains something else, then we should ignore it. Okay, so whatever I just said, we want to formalize all these things. So a deductive calculus is a set of axioms together with some rules of inference. And there are multiple deductive calculi for propositional logic, but the one I'm going to follow today is Hilbert style calculus. So these axioms are the statements, as we discussed yesterday, these are the statements we don't question. So in our case, these axioms are going to be some tautologies. Okay, so for all formulas STU in SL, we have the following axioms. So these are actually axiom schema. Yeah, these are axiom schema that for, so this is not a single axiom. S implies T implies S is not a single axiom. It is actually a collection of axioms indexed by these triples ST and U in SL. Okay, so you can easily verify that this is actually a tautology. No matter what values these the propositional variables, what truth values they get, this formula will always be true. Please verify this for yourself. So this says that S implies T implies S. So anything, yeah, this T is arbitrary, and that will be quite useful. Then second one is kind of distributivity. If S implies T implies U, implies that S implies T implies S implies U. The third one is double negation elimination. Yeah, you are eliminating this double negation and concluding S from that. Whereas this LA4 is about the contrapositive. So the contrapositive of a statement proves the statement. Yeah, I mean, it implies the original statement. Okay, so these are our logical axioms, and there is only one rule of inference that we will take, and that is the modus ponens rule. So, yes?
So the very first one, LA1, so that means the truth value of S decides the, decides what? T implies S. So I was not clear about it.
No, it is a formula. It is a formula. I'm saying that S and T are formulas. There will be some prepositional variables which occur in them. But it doesn't matter what truth values those prepositional variables get. This statement will always be true. This particular formula will always be true. Do you want to verify it?
Sir, actually, T implies S part was clear, but S, I mean, what is S doing? So S implies T implies S, T implies S, I get. T,
what do you mean by you get
there's
it?
something in T? Okay, so, I mean, I get what is meant by T implies S. Like in the LA2, the right hand side is S implies T, implies S implies U. So the left hand side implies the right hand side. And in case of LA1, like what is, I mean, I cannot get a condition.
You are actually thinking too much about it. It is just a formal expression. Yeah, S implies T implies S. It's just a formal expression which is formed out of formulas. Now, S could be very complicated, T itself could be very complicated. What you are interested in is what is the truth value that this statement gets under any valuation. So suppose S and T happen to be prepositional variables. Then can you determine the truth value of this? So let us say I give you the assignment that S is true, S gets value true and T gets value false. Okay, so let us verify this. So T gets value false, so false implies true is true, and this is true, so true implies true is true. So this entire formula gets truth value true. This is a tautology. Then if S gets value false and T gets value false, then false implies anything is always true. Yeah, we are just worried about what values it gets. It only gets truth value true under any valuation. That is the meaning that it is a tautology. And so are the rest of the statements. They are all tautologies.
Yeah.
Yeah, so they don't really mean anything right now.
Okay, sir. Okay.
Yeah, they are just formal expressions, and we have selected a set of tautologies, and that set is sufficient to generate all other tautologies. And what I mean by that will be clear very soon.
Okay, sir. Okay, sir.
So, any other questions about this? What tautologies and... Okay, so these are the axioms which we have to accept without questioning. And yeah, I mean, they are all tautologies, so we should be happy to accept them. Now, this second part, happiness, is just our psychological thing. Yeah, it has nothing to do with mathematics. And there is one rule of inference, which we call modus ponens, that if you have any two formulas, S and T, and you have previously concluded S implies T and S, then you can conclude T from it. Again, like this is a syntactic way of saying something in the meta language, that if S follows, which means S is true and S implies T is true, then can you conclude something about the truth value of T? It has to be true because of the way how implication is defined. So this is just a rule, yeah, rule of inference, that given and yeah, I mean, let us have some patience until I come to this definition of a formal proof. And then you will see all these things connecting with each other. So let us say capital S is a subset of propositional formulas, and small s and t are two propositional formulas. And we will say that S single turnstile symbol T is a sequent if one of the following is true. Okay. So S implies S. So anything that is already present in capital S, that can be derived formally. Yeah, sequent means T can be derived formally from S. So everything that is already present on LHS, you can derive formally from LHS. That is a non-logical axiom. Yeah, there is no logic behind it. You chose capital S, and therefore anything in capital S can be derived. Therefore, non-logical axiom. Then, if T is a logical axiom, then you shouldn't question it. No matter what capital S is, you should always be able to derive T from S. Even if S is empty, you should be able to derive it. And if we have already obtained sequence of these two forms, that capital S derives S implies T and capital S derives S, then capital S derives T. So the third condition depends on the previous sequence. So what is a formal proof? It is a finite list of sequence. Okay. So we start with either a non-logical axiom or a logical axiom, and then in the next step, if appropriate, we can apply this modus ponens rule. And these are the only three types of sequence which you can get. And that is a formal proof. So once again, I want to highlight, like, this is important everywhere in what Professor Rao is doing or Professor SMS is doing. Yeah, that if you have, if you think about a formal proof, then it is a finite list of sequence, and if you are only worried about the right-hand sides, then right-hand sides are formulas themselves. Formulas are finite in length, and a formal proof is a finite list of sequence. So only finitely many formulas appear on the right-hand side of that formal proof. Yeah, so this finiteness will be important, Ramakrishnan.
But the LA axiom, logical axiom, you mean the above four, LA1, LA2, LA3, LA4?
Yes.
What?
Yes.
Okay.
And
yeah.
For any, like, you can substitute anything for ST and U.
Okay.
Yeah, there is no control over that. It is an axiom schema. Okay, so yeah, I have written a simple exercise that verify that all logical axioms are actually tautologies. This will be important very soon. Okay, so let us look at one example of a formal proof. So what are we given? We are given that our language consists of three propositional variables, and we want to show that P implies R can be derived from P implies Q, comma, Q implies R. Now, writing down this formal proof, like these three rules, yeah, whatever we had, those can be taught to a computer. Yeah, you can ask the computer to select anything on the left-hand side. You can ask the computer to generate anything which looks like a logical axiom, which is a logical axiom. And you can ask the computer to deal with modus ponens. But in practice, in reality, it is really very hard to come up with these proofs. Like, this is a very simple thing. Yeah, it looks like transitivity. P implies Q, Q implies R, then P implies R. But the proof for that, yeah, this is the proof. So P implies Q and Q implies R. There is a non-logical axiom that Q implies R. Yeah, because it belongs to the left-hand side. You had to number all the lines, and then you had to write a reason on the left hand at the end for each line, how it follows. Now note that the first line can never get modus ponens as the reason. It has to be either a non-logical axiom or a logical axiom. Yeah, only after line 3 and onwards, only line 3 onwards, you can give reason as modus ponens. Okay, so let us understand this example carefully. So Q implies R and P implies Q. They both can be formally derived as non-logical axioms of this set. But then you have LA1, which says that if Q implies R implies P implies Q implies R. Now you look at this. You have Q implies R in step 1, and you have Q implies R implies something in step 3. Then you can apply modus ponens to conclude the right hand side part of the implication in line 4. And the reason is that you have applied modus ponens 1 and 3. Okay, in the next step, what we do, we take LA2 appropriately chosen, like P implies Q implies R implies P implies Q implies P implies R. And once again, you can use this second part, the non-logical axiom application here. P implies Q. This one, fourth one. Use the fourth one and the fifth one to conclude the right hand side here in line 6 by using modus ponens on the previous 2 lines. And then finally, you use this P implies Q, and you can conclude P implies R from modus ponens on lines numbers 2 and 6. So what is the tricky part? As you would have observed that NLAs are not the tricky part, MP is not the tricky part. Choosing the right formulas S and T and U, yeah, S, T and U in these logical axioms is the tricky part. And for that you have to just use some experience, like experience helps with these proofs, formal proofs. Or you can ask the computer to try and generate all proofs until certain length and try out all these things. Yeah. Okay, so any questions about how this formal proof goes?
Sir, the set S can be infinite?
Yes, set S can be infinite.
But then how do we just... Oh, so the length is the number of lines we write. It doesn't matter whether the...
Length is the number of lines we write. Yeah, so therefore some authors also prefer to omit the left-hand side.
But we want to know what is on the left. Oh, we are not going to set anyway.
Yeah, I mean, we are not worried about how many elements lie on the left-hand side. There is one key result that we will see. It is the finite character of proof. Yeah, if you are interested in that, let us directly go there. Yeah, since the collection of all non-logical axioms appearing in a formal proof is finite. Yeah, because there are only finitely many lines, so only some of them can have the reasoning as NLA. So therefore, finite character of a formal proof, that suppose T is a formal consequence of S, then there is a finite subset which has the same logical consequence, so same formal consequence.
And then we can think about what is the minimum such.
Yes. Yeah, so this finiteness is also important. Actually, this is the main reason why compactness also holds. We'll see that tomorrow.
And so one more question: are we when we talk about proof, we are always going to prove statements which look like this S and that I'm sorry, the symbol T?
Yes, I mean, if you don't have any assumptions, then you can only prove tautologies.
Sorry?
Yeah, if the LHS is empty, then you can only prove tautologies.
Yeah. So we are going to prove when we talk about proof in this setting. The statement
this is a formal proof. Yeah.
Yeah. So the statement of formal proof is going to prove will look like this: some set S and some statement T.
Yes. Yes. So T follows from S. See,
follows.
in mathematics, you don't have anything absolute. Everything is relative. If capital S, then T.
Yeah.
Yeah. So everything is a conditional statement. The unconditional statements are these undeterred truths. Yeah. So for example, S implies S. Yeah. S implies S, that is a tautology. But in order to prove this simple tautology, you still need 5 steps. Yeah, I'm going to give you some exercises soon. I mean tomorrow, to write down formal proofs, and you had to use lot of imagination and lot of trickery to come up with what LAs you should use and where exactly. Yeah, that needs a lot of experience. Right. So again, like I'm not going to explain this proof because in formal proofs there is nothing to explain. It's just that you have to find the right things. But Deepanvita.
Yes, sir. Just a small question regarding this lemma, which says
Mhm.
finite character of a formal
Yeah.
proof. Sir, in this, if we suppose the set of S to be like the formulas, and then from there we are deriving T, so isn't it true for any finite subset of S not of S? Like in this lemma, it is written that there is a finite subset S naught in S, such that from S naught we can get T.
Yeah.
So is it not true for every finite subset of S naught, since it is true for
Okay.
S?
Wait. So let us have a look at this proof again. So I choose the empty subset of the left hand side. Can I prove this?
No, sir. Like if we
Yes.
take the empty subset, okay. Okay,
Yeah.
that.
Or
Yeah.
even if I choose any one formula out of this, can I actually prove this? That P implies Q proves P implies R. Yeah, that doesn't make sense.
That okay. Okay, I got.
Yeah.
Thank
You
you.
need certain things. Yeah. You need the formulas which are required in this proof. So therefore there exists. Yeah, there is a finite subset. Yeah, not for all.
Okay, thank you, sir.
Okay. Any other question? Yeah, these are important things.
Sir, so if we want to prove something in the Hilbert calculus, we have these, let's say, 1, 2, 3, 4, 5 lines of proof. Can we say that there are only finite ways to prove something? Like most of the proofs are equivalent?
Sorry, say that again.
Is there, can we deduce that the ways to prove a statement, like different ways to prove the statement, are all equivalent?
Oh, you are entering into proof theory.
Okay, I don't know about that.
Yeah, so I mean, as long as we have a proof right now, at least for this course, we will not care.
Okay, sir.
Yeah, we'll worry about whether there exists a proof or not.
Okay, thank you.
Yeah, so this part, this lemma, I'm not going to explain anything. Yeah, there is nothing to explain. You will get some exercises tomorrow to actually try and prove certain things formally. But like before going ahead, I want you to think about this. Yeah, I want you to think about this idea of a formal proof. Whenever you write a proof in mathematics, then it also has finite length. You don't write an infinite length proof. Similarly, you only use finite amount of information at a time, like the finite character, finite amount of information to conclude a single statement. And for example, if you prove a certain statement about vector spaces, then you are using some properties, the defining properties or defining axioms of vector spaces. So there are some logical axioms, some non-logical axioms involved. So your statements look like this. So non-logical axioms in the case of a statement about vector spaces are all the assumptions that you have that V is a vector space. and let us say it is finite dimensional. So all those statements are your left hand side, and then you are proving certain statement. So every proof that we write in practice is actually of this form. It's just that the formulas are more complicated. Yeah, so right now we are just doing the bare minimum, the propositional logic part. In the next half of the course, we'll look at predicate logic or first order logic, and that will have much more to say. Yeah? But the notion of a formal proof will not change. It will be a finite list of sequence. And a sequent will again be of this form, and there each formula appearing will again be finite. Yeah, so this finiteness is heavily utilized, and SMS will also use this finiteness to arithmetize, yeah, to girdle number formulas and then proofs, sentences and then proofs and everything. Yeah, right. So again, one more thing which could be slightly counterintuitive when you look at it yeah, from a philosophical perspective, but this is what our logic is, that if you have S and T as sets of propositional formulas where T contains more propositional formulas, yeah, possibly more, yeah, T is a superset of S. And if you can prove little t formally, if you can deduce it from S, then you can also deduce it from T. Okay. And yeah, what is the thing? You simply use induction on line number of proof of S proves T. You replace the left hand side of this by T. Yeah, nothing will change. Correct? Yeah, Shashank?
Yes, sir. So what is counterintuitive in this?
Oh, I mean, not if you think about something, yeah, like person X is good. If that is your data set, that is your capital S, and the next data point you add is that the person X is not good. Then do you still want to conclude that the person is good?
Okay.
Yeah, philosophically we don't do that. Like if you update your information as you go along, but propositional logic doesn't care. Yeah, even if you add something more, it will still prove all the things which it proved earlier.
Okay. And it will also prove the thing that we just added. So
yes, yes. Yeah, I mean, we will have some names for this, like inconsistency. If it proves a contradiction, then we will say it is inconsistent.
But Amit, is not a proof in X a proof in T, obviously. If T contains X,
yeah,
then every non-logical axiom of X is also a non-logical axiom of T.
Yes,
so every proof. So this is just obvious. Why do we have to use induction and such? I didn't understand what I was trying to say about the proof, that use induction on line numbers of a proof of
I'm just trying to say that all the three different types of sequence which we wrote, in all those sequence, we can replace the left-hand side by T. That's all.
That's all. So no, just go back to that slide, and I myself got confused. You see, wait. Here. Why did you use this line? I mean, induction on line number of a proof of this.
Because modus ponens depends on the previous ones.
No, what I am saying is that for this one, monotonicity theorem, what you call, if X is a subset of T, then every non-logical axiom of X is also a non-logical axiom of T, and therefore every proof in X is a proof in T. What is that?
The thing is that I have defined it in a specific way that if I have sequent capital S proves S implies T and capital S deduces S, then I can conclude capital S deduces T. So if I want to replace everything on the left hand side like by T, then I need sequence of the form capital T proves S implies T and capital T proves S, then I will get capital T proves T.
Okay, you go ahead.
Yeah. Okay, so now this, yeah.
In that example you had just before this, can you go
Okay,
there?
yeah, sure.
Yeah,
This one?
so we are proving P implies R. So if in the set S, that is P, PQ and QR, we also add not of P implies R, even
Yeah.
then this proof is valid.
Yes.
Okay.
Yeah. Because that is our definition of a formal proof.
Okay.
Yeah.
Hmm.
And
So
yeah, it is not surprising. We are just deducing something formally. So we choose a finite subset of our non-logical axioms and we deduce something using an algorithm. So there is nothing paradoxical here. Yeah.
But then it won't relate to our semantical definition.
No, it will. Wait for that. Yeah, that set will be inconsistent. It will prove contradictions.
Oh, okay.
Right? Yeah, we have taken care of that in the next part. But before I go ahead, I want you to look at this important property. Yeah, that if S is a subset of SL and S and T are two propositional formulas, then capital S proves small s implies T if and only if you can pass it to the left hand side, pass this small s to the left hand side and still prove T. So this transfer across this single turnstile symbol, now I want you to remind of this particular exercise. Yeah. So we did that using double turnstile symbol. Now we are doing it using a single turnstile symbol, like formal consequence. This was a logical consequence. Okay, so let us have a look at that. The proof is long but very straightforward. In the proof of, so suppose you have this, yeah, S proves S implies T, then use monotonicity to replace the left hand sides of each line to get this. So you will have this sequent, then you add these two sequents. Yeah. So you can add this because it is a non-logical axioms. Yeah. Then you can apply modus ponens to conclude T. Yeah, earlier you only had capital S on the left hand side. You can add this small s, yeah, S union singleton small s to that and still do the proof. So this is one side. For the converse, actually, we need something more. Yeah, we need to use induction on line numbers. So I will just give you a glimpse of the proof that suppose your line is of the form logical axiom. Yeah, but now the left hand side of that line of that sequent is S union singleton S, and this is the ith line. Yeah, that proves Ti, and Ti is a logical axiom. Then you have replaced this line by these three together. Okay, S proves Ti, then S proves Ti implies S implies Ti, and S proves S implies Ti. So you just replace this single line by these three new lines, and you have a proof of, you have replaced the ith line by the corresponding required line. Yeah, the original one was S union singleton S proves T, and we wanted to get S proves S implies T. So you have given a recipe for converting this proof into this at ith line. And for non-logical axioms and for modus ponens, yeah, how to do it, I have written in detail in this proof. It is not at all difficult, but it is just tedious. You just have to use appropriate logical axioms at appropriate times. And the last line of the original proof was S union singleton S proves TK, proves T. And in the new proof, it will be this. So that we can convert it into a proof. So once again, understand that formalism is all we care about while dealing with deductive calculus. Okay. We are not worried about anything else, like not about the meaning, etc. Like intuitively, this statement is very simple. Yeah, you are just transferring formulas from the left hand side to right hand sides freely. And once you have proved this theorem, deduction theorem, then you can freely use this deduction theorem as a derived rule of inference. So far, we had only one rule of inference, that was modus ponens. But you can also use deduction theorem as a derived rule of inference because you have used it, you have proved it already. So any questions so far about this? Okay. So now I'm going to just give you a series of lemmas. Yeah, they are just formal deductions of something. And the proofs will be left as exercises. The proofs are long. But yeah, you can see that whatever I'm trying to prove is a tautology. I will derive various tautologies. So for example, S implies negation, S implies T. So at the end, we want to apply the deduction theorem. So, I mean, we start with a proof of, we want to obtain a proof of T from S comma negation S. And even though I haven't defined what is inconsistency, you have some meaning associated to that English language word. And you can see that S comma negation S should be able to prove everything. And that is what this says precisely. Yeah. T is anything which has no connection with S whatsoever. And you can prove T from S and negation S. Yeah, you can derive anything, yeah, any garbage from an inconsistent set. That is the meaning of this. Yeah, so this is a formal proof. I'm not going to explain this, or I'm not going to prove these things as well. So proofs are left as exercises, and you can use DT as a derived rule of inference. But what do they say? Yeah, for example, yeah, I mean, lemma phi is just a dual version of this. Instead of S and negation S, you use DT at different times. Then this is double negation introduction. We had double negation elimination as a rule of, as a logical axiom, but we can also prove the other way, double negation introduction. Yeah, I mean, yeah, there is nothing to see here as such. But
what is the meaning of, like, for example, lemma 4? What is a set on the left hand side?
The set on the left hand side is empty. So that's why I said these are all tautologies.
Okay, so which we can just derive using whatever we have.
Yes, only using logical axioms. There are no non-logical axioms here involved here.
Okay.
Yeah? I mean, even though you can see non-logical axioms here, I am actually using deduction theorem. And in the proof of deduction theorem, you can see that you can convert these non-logical axioms to logical axioms. You have an alternate proof of this without having this doubleton set on the left hand side. With the empty set, you have a proof. Okay, so these lemmas are not that important. They are just some formal tools required in the proof of completeness theorem. A set S of propositional formulas is inconsistent if you can prove anything from S. Yeah, this is the definition of inconsistency. Yeah, for all T in SL, there is a proof of T from S. I mean, you just saw that S comma negation S, this doubleton set is inconsistent because it can prove anything. And this is what this example says. And S is consistent if it is not inconsistent, which means there is some T in SL for which there is no proof from S, no formal proof from S. Yeah. So consistency and inconsistency, I would like to go back a bit and remind you of this. Unsatisfiability is inconsistency. whereas satisfiability is consistency. There exists some valuation, and this is precisely what completeness theorem will say. A set is consistent if and only if it is satisfiable. Yeah, so we'll have to produce this valuation. I will directly go to the next thing. Yeah, so in the next 2-3 lemmas, we are just going to look at some reformulations of inconsistency. So a set is inconsistent if and only if you can prove a contradiction. Like S implies S is always true. It is a tautology. So negation of S implies S is a contradiction. So you can prove a contradiction from S. Yeah. So one side is very clear that you can prove anything. So in particular, you can prove this. And you can use lemma 1 and lemma 5 to get a formal proof of S proves T from this. I'm not going to say more about it. This is a good exercise. This is a very short argument. Yeah, just 3-4 lines of formal proof. Again, now look at this. So S union singleton S is inconsistent if and only if you can prove negation S from S. Now the proof of this is given in terms of formal proofs, but I want you to compare this statement with what we had earlier. Yeah, for the semantic part, what we said here, that S has T as a logical consequence if and only if S union negation T is satisfiable. So this was the same statement with double turnstile. Yeah, possibly negations swapped, but negations don't really matter. Yeah, you can put negation T here and T here. Doesn't matter. Because double negation is same as no negation. Yeah, so this proposition and this lemma, they are the same. Yeah, S union singleton S is inconsistent, defined only if you can prove this. Negation is from that. So inconsistent means that you should be able to prove something that contradicts. So it is like splitting this left-hand side into two parts. So the first part can prove something that contradicts the second part on the left-hand side. That is what we mean here. And the last thing that we need is that, I mean, that is again something very intuitive, that if you can prove a formula as well as its negation, then our set is inconsistent. Yeah, I mean, use lemma 2 very simply, that if you can prove S, if you can prove negation S, and then you can apply MP twice to get a proof of T, where T is arbitrary. And this is inconsistency. So any questions so far? Are people listening?
Yes.
Yeah, so inconsistency is very similar to unsatisfiability, and consistency is like satisfiability. And these are just some formal lemmas. We wanted to deal with these things because now we are ready to show that the single turnstile symbol and the double turnstile symbol have the same meaning. Which means what? So first part is the soundness theorem. It says that if you can prove something from S, you can derive something as a formally from S, then it is actually a logical consequence. So this part is quite easy because you only have to go through the steps of that formal proof, and at every step you had to ensure that the right hand side is also true whenever the left hand side is true for a given valuation. So that is what I have written. Yeah, suppose S proves T and V is a model of S. Yeah, that means V makes everything in S true. We want to show that V of T is true by induction on line number of the formal proof of T from S. Okay, so induction hypothesis is that for each line of the formal proof, we show that whenever V of LHS is true, then V of RHS is true. Again, like base case is simple, that if the reason is logical axiom, then RHS is a tautology. So it is always true for any valuation. If the reason is a non-logical axiom, then any valuation which makes LHS true will also make everything in that LHS true. Yeah, that is the definition of V of LHS being true. And therefore, RHS is also true because RHS belong to LHS. And the induction step is that, so you have two previous lines where you have modus ponens. So let us say Ti, I and J were the previous lines where you prove Ti, and for line K, yeah, where we want to prove the induction step, for line K we have Tk. So therefore line J must look like Ti implies Tk. The right hand side of line J must look like this. So we have Ti on the left right hand side and Ti implies Tk on the right hand side, and you want to prove Tk. So now simply use what is the meaning of the valuation of an implication being true. That's all. Yeah. So we have V of S is equal to true. By induction hypothesis, the Ti gets value true and Ti implies Tk gets value true, and therefore Tk also gets value true under that valuation. So that's all. So this is a very simple proof by induction. So soundness for any logic is usually, for any deductive system, is usually the easier part. Yeah, it is always the easier part. Whereas completeness, yeah, so just think about it philosophically, what we are about to say. That if T is a logical consequence of S, then there exists a formal proof of T from S. So formal proofs are these beasts. Yeah, you have no control which logical, you have to do lot of trial and error. At least a human has to do lot of trial and error to come up with a particular logical axiom. But completeness theorem will guarantee that, okay, if you have verified the semantic condition, then actually there exists a proof. Okay, so this is the interesting part. And whatever you have been learning in the set theory lectures by Professor Rao, we are going to use that. We cannot prove this without using axiom of choice. Yeah, axiom of choice will guarantee existence of a proof, formal proof of T from S whenever T is a logical consequence of S. So any questions once again before we start with, yeah.
Sir, can you please go back the soundness theorem?
Yes.
Yes, so can you just repeat this? Suppose S implies T, this one, and the base cases.
Okay, okay, fine. So this is a formal, so T is deducible from S, which means there is a formal proof. A formal proof is a finite sequence of sequence. Yeah, finitely many sequence appear in that formal proof.
Yes.
So we have a proof. And let us say that V is a model of S, which means V makes left hand side true. So in order to show that T is a logical consequence, under this assumption, we should show that V is also a model of T. Yeah, so we would like to show that T gets truth value true under this same valuation V, which makes S true. And we will use induction. The base cases are two. If the reason is a logical axiom, then the right hand side is a tautology. So tautology means every valuation will make that true. So our choice of V doesn't matter. Similarly, if the reason is non-logical axiom, then the formula on the right hand side is actually one of the formulas on the left hand side. That is how we describe non-logical axioms. And therefore, any valuation which makes LHS true will also make the RHS true.
Sir, this non-logical axiom and the axiom part, the logical axiom part.
Right.
Where, I mean, if the reason is LA, then RHS is a tautology, this one.
Yeah.
And if the reason is NLA, then then whatever you said, how do you?
Whatever I said means that, okay, so let me remind you, let us go back a bit and let me remind you what this means. A non-logical axiom is anything which already appears on the left-hand side. So if a valuation makes everything in capital S true, then it should make small s true. That's all I said.
Yes.
Okay.
Yes.
Any other questions? Okay. So let us go to the proof of the completeness theorem. There are two versions which we will show. The first version is that suppose S is a consistent subset of SL, then there is a valuation V, which is a model of S, which means S is satisfiable. So consistency implies satisfiability is our first version of completeness. And what is the proof strategy here? So satisfiability implies consistency, that is soundness theorem. Yeah, just make sure, like after some thinking, yeah, it is not immediate, after some thinking, you convince yourself that satisfiability implies consistency. It follows from soundness. Right. So what is the proof strategy? That we start with a consistent subset and we will use Zorn's lemma to construct a maximal consistent set containing S. And this maximal consistent set will be used to define a valuation which is a model of S, which means that valuation will make everything in S true. So I hope everybody is familiar with Zorn's lemma now. Yeah, Professor Rao covered that in detail in his lectures. Yeah, it is an equivalent statement of the axiom of choice. So, okay, so if you are familiar with that, then let us directly start. So let gamma be the set of all subsets of the set of propositional formulas which are consistent and which are extensions of S. Yeah, very standard technique in mathematics, that if you want to show maximality of something, then you start with all extensions and you verify the hypothesis of Zorn's lemma. So the first hypothesis of Zorn's lemma is that the poset has to be non-empty. Yeah, so first I should describe what is the poset. The poset is this: gamma with subset relation. Yeah, so subset relation is our order. So this is a partial order on which we are going to verify the hypothesis of Zorn's lemma. So first of all, gamma is non-empty because S is itself a consistent extension of S. So this is non-empty. Then next thing is that suppose delta is a chain or total order, yeah, in gamma, then we would like to claim that the union, yeah, remember that gamma consists of subsets of SL. So union of delta, yeah, union of any subset of gamma will again be a subset of SL. And clearly that subset will contain S because every element in delta contains S. So T will contain S. So what remains to show is that T is consistent. Then T will belong to gamma. And you can see that this union of delta is an upper bound for delta. So if we prove the claim, then we will have shown that every chain, every total order in gamma has an upper bound. Therefore, by Zorn's lemma, there exists a maximal element, which we can use for our purposes later on. So first part of the proof is that we would like to show T is consistent. Okay. So our proof goes via contradiction, that if, suppose on contrary T is inconsistent, then what will happen? That T can prove a contradiction. It can prove that negation S implies S. This is a contradiction for some S. Now, using finite character of formal proofs, this is a very crucial step here. There exists a finite subset T prime of T which has the same consequence. Okay, T prime proves negation S implies S, because we use only finitely many non-logical axioms in this proof. Okay, now comes another important point, that because delta is a chain and T prime is finite, so choose first element of T prime, let's say let's say U1. So U1 will belong to some element in delta. U2 will belong to some element in delta. So let us say that they are labeled T1, T2, Tn. So you can take the largest of them. So T1 union T2 union Tn. And because you are only talking about finitely many of them and delta is a chain, there exists some T double prime in delta which contains T prime. So by monotonicity, T double prime proves a contradiction, and again by the same lemma, T double prime is inconsistent, which is a contradiction. So the union has to be consistent. We prove the contrapositive. If T is inconsistent, then we obtain the contradiction to the fact that delta is a chain in gamma, where gamma consists of consistent sets, consistent extensions of S. Okay, so this is a very standard piece of proof in mathematics. But still, if you have any questions, feel free to ask me now.
Can you explain this proof by claim? I didn't get that.
What part did you not get?
So if T is inconsistent, then it's a starting part. Why are we using this? I didn't quite get the whole idea.
No. So this is lemma 7. We have derived various consequences. So a set is inconsistent if and only if it proves this particular contradiction for some S, for any actually S. So a set is inconsistent if and only if it derives a contradiction. So that we are using. So if we assume on the contrary that T is inconsistent, then we can derive a contradiction. Then in the course of the proof of the claim, what we show is that one of the elements of delta itself was inconsistent. Which is
Got it, sir.
Okay. Any other questions? Okay. So let us go ahead. So by Zorn's lemma, there is a maximal element of gamma, let's say T naught. Right. Now we define a function on SL, a valuation, which simply partitions it according to whether it belongs to T naught or not. So we'll say that valuation of a particular formula is true if and only if it belongs to T naught. So you have looked at the notion of ultra filters, filters and ultra filters. So this T naught is actually the congruence classes of formulas in T naught, that is an ultra filter. So ultra filter partitions the set into exactly two parts, partitions the entire Boolean algebra into exactly two parts. That exactly what we are going to say. And a valuation assigns value true to half of the formulas and false to remaining half of the formulas. And how do we decide that a formula U gets value true if and only if its negation gets value false. And if you remember from a characterization of ultrafilters, then a filter is an ultrafilter if and only for every subset, either that subset or its complement belongs to that ultrafilter. So that is exactly the same statement. But anyway, I mean, if you haven't understood ultrafilters properly yet, no issue. We can go to the proof. The proof will not depend on something being ultrafilter. So first claim is that T0 is deductively closed, which means what? That T0 proves U if and only if U is already present in T0, if and only if it is a non-logical axiom. So everything that can be proved from T0 is a non-logical axiom. That is meaning of deductively closed. And this is simple application of maximality. Yeah, that this is a maximal consistent subset, which means if you add anything extra, yeah, it is on the verge of breaking. If you add anything extra from outside, then it will break, which means it will become inconsistent. Okay, so that is what the proof says, that if U is in T0, then T0 proves U by non-logical axiom. Yeah, this is NLA, this is one side, that is not hard. On the other hand, if U doesn't belong to T0, then T0 union U is inconsistent by maximality of T0. Okay, you cannot add anything outside because it was maximal to begin with. So it is inconsistent. So by lemma 8, you can show that T0 proves negation U. Right? You have a proof of negation U. We saw this lemma. Yeah, this lemma was crucial.
Yes,
We saw the proof of the semantic and the syntactic version. And since T0 is consistent, lemma 9 guarantees that T0 does not belong to U. Yeah, lemma 9 says that if you can prove S as well as negation S, then you are inconsistent. So if you can prove negation U, then you cannot prove U. That is lemma 9. So again, like, because we have support of all these previous lemmas, this proof is simple.
So can you tell what is lemma 8 again?
Yes, so I will go there. Yeah. Lemma 8 says that S union S is inconsistent if and only if it proves negation.
Okay, yeah.
And lemma 9 says that if you can prove both S and negation S, then you are inconsistent. And the contrapositive of that will be that if S proves S and S is consistent, then S cannot prove the other one.
Okay, sir. Thank you.
Yeah, it cannot prove both of them simultaneously. So that is what we have done here. Yeah, lemma 9 guarantees that T0 doesn't prove U. Okay, so after proving claim 1, what remains to show is that whatever function we have defined here, that is a valuation. Yeah, valuation means what? I will go back, yeah, to the definition of a valuation. So what we said, that a valuation is a function which satisfies these two properties, that V of negation T is true if and only if V of T is false. And for the implication, now we are not using conjunction as our connective, we are using implication. So either V of T is false or V of S is true. Yeah, this is true if and only if. Now combine these two conditions with the definition of valuation. Yeah, how did we define this particular valuation? We said that some formula gets valuation true if and only if it is in that maximal consistent set obtained from Zorn's lemma. So claim 2 and claim 3 are precisely those two statements. Yeah. So let us look at claim 3 first. So T in SL, T in T0, if and only if negation T is not in T0. So this is the valuation condition for negation. And similarly, S implies T is in T0 if and only if S is not in T0 or T is in T0. So if and only if S is false or T is true. So we have just written these two claims. Okay, I will just do one of the claims because we don't have time, and the rest of the claim I will leave as an exercise. Yeah? I mean, not as an exercise, for you to read. Yeah, I have written the proof here. So clearly, both T and negation T cannot belong to T0 in view of claim 1 and lemma 9. Yeah, lemma 9 says that you cannot prove both of them, and proving something is same as belonging. So therefore, both of them cannot belong. So T and negation T cannot belong to T0. Now, if T doesn't belong to T0, then T naught union singleton T is inconsistent in view of maximality. Then by lemma 8, we have a proof of negation T, which means negation T belongs to T0 by claim 1. Yeah. So first we argued that both of them cannot belong, and then we argued that if one of them doesn't belong, then the other one does. If T doesn't belong to T0, then negation T does belong to T0. Yeah. So that is what we needed to show for proof of claim 3. Proof of claim 2 will use some lemmas. Yeah. So lemma 6 and monotonicity, etc. So they will be used. But again, it is not difficult. Yeah. This is just these 6 lines, and I will invite you to read about this. Read this proof. So what we have shown so far, that if you have a consistent set of formulas, then it is actually satisfiable. And in the next lecture, we will prove completeness theorem version 2, which says that if T is a logical consequence, then you have a formal proof. Yeah. So again, the proof is very simple, that if T cannot be proved from S, then S union negation T is consistent. And hence, by the first version of completeness, also satisfiable. And you can take a model of, because it is satisfiable, you can take a model of S union negation T, which means this valuation witnesses that S is true and negation T is true, which means S is true, but T is false, which means T is not a logical consequence of S. Yeah, I mean, I already covered completeness theorem version 2, but yeah, I will leave compactness for tomorrow, and I will give you some exercises about compactness in the tutorial session tomorrow, and some other exercises about propositional logic. So yeah, we have some minutes left. So can you ask questions now, if any?
So the version 1 and version 2 together, they give it a if and only if kind of condition, right? So
yes.
between proof and truth.
No.
Okay.
So soundness and completeness together give an if and only if condition.
Okay. Yeah.
These are just two different versions of the same theorem. Completeness theorem version 1 and version 2. Yeah, Shashank.
Yes, sir. So I have two questions. So the first one is about the choice of the axioms and rules that we took for this Hilbert calculus. So, sir, was it so this choice was made because we wanted to establish the completeness theorem? Like, is it is this choice based upon that we want our system to have some properties, basically complete?
Basically completeness.
Okay, but we can have other.
Yes, there are other calculi. Yeah, there is natural deduction system for propositional logic, which is also popular, and it is extremely difficult to write formal proofs in Hilbert style calculus, but very easy in natural deduction system. The point of me choosing Hilbert style calculus is that the proof of completeness becomes easier with this.
Okay.
For natural deduction system, you have fewer logical axioms, but more rules of inference.
Okay, and sir, in that system, do we have a kind of correspondence between the rules here and the rules there, and the axioms here and the axioms there?
They are equivalent.
Okay.
Yeah, those proof systems are equivalent because they correspond to the same. Like both proof systems will have completeness, soundness, and completeness, and because our semantics hasn't changed, you can see that these two different proof systems are equivalent.
Okay, so they prove exactly the same things.
Yes, they
if
prove
we
exactly
fix
the
set
same.
S.
Correct, correct.
And sir, so the second question is, if we just focus on one system, for example, this Hilbert style calculus, and what we do is, instead of taking LA3, we remove LA3, and instead of that, we add a rule of inference that if we have not S, then we can derive S.
Yeah.
So what we have done is, instead of we have deleted an axiom and kind of put a similar rule of inference. So
okay,
will we get the same? Can we derive the same formulas, or
I think yes. Like I think yes, because ultimately you have deduction theorem. It's like transferring something to the left hand side.
Okay. So here also it means that we can delete axioms and instead put them in rules.
But okay, again the point is that you should add one such rule of inference for all S. Yeah, logical axioms are schema. Yeah, they are indexed by S, T, and U. So you have to put once. I mean, yeah, if you can prove double negation of something, then you can prove that formula. Yeah, that is the rule of inference for all S and T, for all S. And that should be possible. I mean, your questions are more related to proof theory, which we are not going to cover here, and I'm not a proof theorist either. So to tell you more. Yeah, from Galaxy Tab A, we have a question.
Thanks.
Are both the versions of completeness proof non-constructive? Yes, that is very unfortunate. And in fact, I would like to add that completeness theorem is actually equivalent to a weaker version of axiom of choice, which is called the Boolean prime ideal theorem. Okay, you can show that it is equivalent.
Equivalent to what?
Equivalent to a weaker version of axiom of choice, which is known as the Boolean prime ideal theorem. I mean, yeah, you have seen something like that, every filter in a Boolean algebra can be extended to an ultra filter.
Yes, sir.
Yeah, this is strictly weaker than Zorn's lemma or axiom of choice. So Zorn's lemma is used to prove this, but you cannot prove Zorn's lemma from this statement. And that statement is equivalent to completeness theorem.
Okay.
Yeah, Ujjwal.
Yes, sir. Am I audible, sir?
Yes.
So in the course of this lecture, at one point, like just after you introduced the axiomatic system here, you said that we using like via these once you establish these axioms, it is possible to write a computer program like given a it is possible to write a computer program such that for a given formula we can like
verify.
It can generate.
No, we can verify whether it is a proof or not. I mean, generating proofs is hard. It's a computer verifiable system.
I thought you said something like it can like keep generating proofs up to a certain length.
Yes.
Something like that.
So yeah, if you can get your required statement as one of those, then you are happy. Otherwise, you don't know. I mean, that is the entire point of decidability. Yeah, whether an algorithm can generate every single statement. What SMS is teaching.
Okay, sir.
Yeah, decidability problem.
So my doubt was that this statement seemed to imply that there is some natural bound on the length of the proof given.
Oh, there is no bound. It just says it is finite.
Okay.
Yeah, no bound.
So that is the only guarantee that it's finite. So we,
yes,
that is the only guarantee that it will terminate.
Yes, yes.
Okay.
Yeah.
So,
Yes.
So can you go to lemma 2?
Yes, I can. Where is that? Here. Yeah.
So, sir, I'm unable to understand. So, the on the left hand side in the statement there is empty set.
Yeah.
But while proving it, you started with s comma not s.
Because I use dt. At the bottom, there is the reason. Apply dt twice to complete the proof. So deduction theorem will help you to transfer this negation s into negation s implies t. Then again, another application of deduction theorem will help you to get this s from this side to that side.
Oh, sorry. Yes. Oh,
Yes.
got it.
Arul, you want to say something about this?
Not much. I mean, it's long since I did the course, but so we did a lot of entitlement. I mean, proofs in
Okay.
two proofs, and most of them essentially used contradiction. So we hardly. I mean, in fact, even like we tried to think of proofs where we could somehow construct, but often contradiction seemed like the most easiest way to go about.
Yes, I think the organizers would like us to stop now. It's well past time. So if you have any questions, like, yeah, you can message me or email me. Yeah, that's fine.
Yeah, then probably tomorrow for the tutorial session also you can address some of them.
Tutorial I will do. I will give you the tutorial sheet. I did not want to disclose what I'm going to teach in predicate logic yet because I wanted to see how this goes.
Okay, all right.
And then I will release the tutorial sheet. Soon.
So you'll do that today or
most likely by the end of today. Yeah.
Okay. So participants have
can I just make one more announcement? At the end of today's tutorial session, we'll circulate a Google form for student presentations. Yeah, just that.
Yeah. Okay. So thank you so much, sir. So we'll break for lunch now, and then we'll come back at 2:15 for the next session. Yeah, thank you.
Sir, could you please upload the list of books that you showed us
right
at
I
the
did.
beginning?
I will.
Thank you.
Yeah.
Okay, thank you so much.
On under syllabus tab. Bye.